the most traditional way and established way of measuring brain activity. So if you want to deal with brain activity data, you have to wonder how to process it. And within this presentation, we'll get into a lot of these things. But just to set the stage of what we often encounter when we deal with EEG data or brain activity data in general is, first, I already mentioned, this data often has a lot of artifacts. So we have to look into ways of signal processing, starting with simple filtering techniques, but also much more advanced techniques such as independent component analysis to find these artifacts and remove them so that we have data which is clean enough to process and draw conclusions from. So this is an important aspect which always comes up when you're looking at brain activity data. And then many works deal with some kind of machine learning techniques, right? So to interpret brain activity data, we often have to make conclusions which may not be obvious from just looking at the data, and their statistical machine learning techniques are often the way to go there to train a classifier, for example, which can discriminate different types of cognitive states, for example. And of course, here also neural networks have emerged in the last years, but also specialized techniques which are dedicated to specific EEG patterns. But in general, machine learning is an important tool if you're dealing with brain data, but not for all. I mean, we also see examples here where machine learning does not play a role. So this field is quite diverse in that regard. So just for this introduction, just to give you an idea of what fields you can expect to see when you're looking at the combination of SAR-based human-computer interaction and the measurement of brain activity. So this is drawn from a small study I did together with a colleague, Erin Soloway, where we looked at how brain data is used in various HCI applications. What we see that there's really a broad range of domains to which this is applied. So a lot of these fields are also fields which are often touched in VR applications. So for example, you say entertainment and gaming are things which come up quite often. So these are domains which in which especially this integration of brain data can be effective, but also many other fields, right? So this analysis doesn't show you all the results, but for example, robot control, we'd see an example there from probably Hakim, and also dedicated VR applications. And there are also lots of specific traits. So if you are interested in what can you actually get out of the brain data, there's also a very broad range of things which people explore when they're recording brain data in HCI. So just to give you an impression there, for example, people are looking at workload. So that's one of the things many people are interested in, right? So measuring during an application in real time, potentially, what's the load of the person? Is the person still relaxed, or is the person maxed out in their cognitive resources? And depending on that, for example, adjusting the application and the task difficulty the person is facing. Another important aspect is engagement and attention. So what aspects of a scene, for example, is the person paying attention to? One of the next presentations by Lisa will be focusing on that to make AR applications adaptive to the attentional state of the person. Other things, for example, relate to emotions or to error feedback. So systems which adjust itself once they notice that some kind of error has occurred. So, for example, a glitch in the application has occurred. The system should adapt to that or respond to that. This is something which you can get out of brain data and what people are looking at. I also already mentioned that there are different ways of integrating brain data into XR applications, and there's really quite a lot going on there. So I'll show you examples of all of these, and again, we basically, I think this whole selection of applications we'll see throughout this workshop. So if there's a certain kind you're most interested in, it's very likely that you will see more on this during this workshop. And for the reasons of time, I'll not go into this abstract analysis, but just show you some of the examples which illustrate well the different use cases. And the first one I want to get started with is explicit control. So we can use brain activity to directly steer or control elements in the XR environment. There are different paradigms of doing that. So, for example, we can use steady state visually evoked potentials. That means we are looking at basically flickering stimuli in the scene and the brain responding to these. We can use motor imagery, so have the person imagine certain movements and try to recognize the associated brain patterns. Or we can again look at responses to specific other patterns in the environment, and we can use this basically to allow people to control their XR environment just by thought control, right? So, for example, on the left, you see an example where a person is controlling their smart home environment just by selecting an option or just focusing their attention on a specific option. On the right, you see an example by Hakim on robot control based on thought commands, basically. So this is one way of directly controlling your XR environment through brain data. Another type of application is mental state assessment. So I already mentioned. Basically, this is measurement of states. So, for example, workload recognition. So if you want to know, is the person currently doing a very difficult task, or is the person doing a simpler task? And depending on that, for example, change how much additional information we give that person, and we can classify our brain data to recognize these traits. So this is mental state assessment, and we can do that for workload, for emotion, for attention-related cognitive processes, and much more. Then the third type of using brain activity data in XR is neurofeedback. So neurofeedback is the most direct type of interactive system or system which immediately uses the data within the application by presenting the measured brain activity either as raw data or as processed in some way to the user in real time. And the purpose of this is it can be very different things. So, for example, for meditation purposes, if you want to give a person feedback of how relaxed they are, for example, can be used for different rehabilitation purposes. So we'll see something on that later in the day, or also for educational purposes. So to, for example, give you valuable illustrations of your brain activity in different settings and conditions. And that's I think very interesting for many in the XR community. We can also use the brain data not only during the actual application use, but also outside of it and afterwards for evaluating the system. So, for example, brain activity tells us a lot about things we want to know to tell us if an application is actually well designed or not. So I already mentioned we can measure workload, and this is of course interesting to see if an application is designed in a way which can be handled by the average user, or which is maybe too overloading. We can use brain activity and physiological measures to capture presence, the feeling of presence, or also breaks in presence. So, for example, we investigated how questionnaires which you apply during an XR experiment break the presence, the feeling of presence of a person, and how we can influence this with different designs of the questionnaires. We can look at system errors and try to isolate these by looking at the brain activity data. And there's a lot of research which tries to predict cyber sickness through the analysis of brain activity and responding early to that, or just to evaluate what's going on there to build better systems. Yep. So neurofeedback already was an example of an open loop or closed loop system, but of course we can use all these systems which you can build offline. So basically in a Posttalk analysis, we can also have in an open loop or closed loop systems, right? So we can have systems which change their behavior based on the measured cognitive states, actually. So not just show what is measured as a neurofeedback, or look at the results post-hoc in the analysis afterwards, but directly in real time responding to that. And just two very brief examples on that would be work by Brouwer et al., where they directly adapted the video preloading in a VR video based on the predicted head movement, which was predicted through EEG, which was actually quicker than looking at the movement data. So it responded earlier and gave more time for video preloading. Or things like adjusting game difficulty, for example, based on the measured engagement of a person. Right? If we know that the person starts to disengage with a training task in VR, then possible to adapt the system and, for example, increase the game difficulty to avoid boredom, or decrease it to avoid frustration. And then finally, of course, that's basically the most traditional discipline, right? Where you want to use brain activity is in various cognitive science experiments. So this is just another example of our research here, where we wanted to find out changes in body ownership perception manipulated through the use of virtual tools. So people were asked to manipulate their environment through the use of virtual tools, and we were interested in how this influenced their body perception. And one way of investigating this is, of course, recording brain activity data. So this is another field where brain activity data and XR come together. And here it's less than that the brain activity helps the XR system, but here it's more that XR gives us the way to create an immersive environment, or an environment which blends real and virtual contents, and where brain activity is then stimulated through this environment, and actually the XR there helps the brain activity based cognitive science analysis there. So again, we see that the interaction works in both ways. All right, and that was it already from my tour de force through a lot of these fields, which you'll see later on over the course of this workshop. So we saw that mixed reality and brain activity can support each other nicely. That this can they can integrate in many different ways through explicit control, mental state assessment, neurofeedback, but also open and closed loop systems, or the evaluation of the XR systems. There are a lot of technical challenges in combining these two complex technologies, starting from the synchronization, actually, how do these work together, to the question of how the electrodes are actually placed on the head when there's already a head-mounted display there. And of course, the limited computational resources we often face, especially if we want to apply AR, for example, in the field. But you'll hear more on these in the upcoming talks. So With that, I want to conclude my introduction. Let's see if there are questions. Thank you for your attention for now. Any questions? Yeah. I guess we can. So everybody can write questions either in the chat or just speak out. I think we're the crowd is maybe not so
big.
Can
you hear me?
Yeah.
So I wanted to ask a question on actually how actually to define, let's say, a baseline for cognitive task, like the cognitive load for specific task.
Yeah, that's a very good question. That's something you always deal with if you're looking at brain activity. And what you usually do is you create experiments in which you can manipulate the process you're interested in a way that you know what the result is. So, for example, you give people tasks of which you know that they are difficult or not difficult or of intermediate difficulty. And use these as basically your ground truth labels. And if your model works well enough on such data, you can hope to also generalize then to unseen data, of course.
All right, thanks.
All right, so if there are no more immediate questions, I suggest we dive into the more detailed presentations of all the other topics. So our next and first presenter is Anatol. Are you here, Anatol?
Sure. Hi, Felix. So the thing is, Anatol is having some troubles with his mic, so he's going to use mine through phone. So it's a bit of a prototype solution, but let's see if you hear him. Anatol?
Yes, thank you, Hakim, for letting me do the presentation via using your microphone and my phone. I hope that my sound is not the voice is not too creepy with the microphone. Felix, can you tell us if you can hear?
I think it's okay, so I can understand you well.
Okay, great. So I'm going to stand by the screen a little bit like this, and then I'll try to share my screen.
So will you use the same screen, the left one?
Yes, I suppose it's if it's working, then I prefer maybe to stick to the same, and so that people don't have to move also in the room. Let's try. Okay, at least this seems to be working. And then...
Yeah, we see your PowerPoint.
Yeah. It's okay?
Yeah, looks great.
Okay, great. So let me start. So I'm really happy to introduce also our work. I'm going to present the research activities that we are developing at INRIA in Rennes, in France, since a little bit more than 15 years, during which we have been working on combining brain-computer interfaces with virtual and augmented reality technologies, trying to build hybrid technologies, mixing these two, and trying to promote novel kinds of immersive applications based on these two types of technology. I'm going to here make a really big picture, to draw a really big picture, and then Hakim, a little bit later on, will make a zoom on a specific works that we have been conducting together with Hakim on augmented reality and BCI. And he has lots of great stuff to show also later. So first of all, I hope that you see the video here in this first slide. If yes, then it means that you are going to be able to see all the videos that are contained in this presentation. So we are located in the west part of France at INRIA, the French National Research Institute for Computer Science. We are a group of around 35, 40 people. And we have been always working since the 90s on the topic of virtual reality. for instance, using these great cave systems that we have in Rennes, this inertia room, this very big cave, 10-meter large that you see on this video. And we started to connect with BCI at the beginning of the year 2000, in 2003, 2004, where we started notably a PhD thesis of Fabien Lotte, who is now a renowned, a really great researcher working in Bordeaux in France on this topic. And with his PhD, we already tried to establish a connection between BCI and virtual worlds. And here is one of the first videos that we shot at this period, where somebody is imagining left or right hand movements to move this virtual ball to the left or right to score goals. And you see vintage stereoscopic glasses and also vintage EEG headset with gel that is mounted on the head of the user. So the BCI activity in our team is now focusing on a general objective, which is the study of human-computer interaction based on these two technologies, BCI and virtual reality. It corresponds to 4 different research topics that we can discuss later on. The first one is how to study and make use of study neuromarkers and use VR as a paradigm, as an experimental paradigm to study neuromarkers in very safe and motivating conditions for the participants, very controlled situations, to study brain neuromarkers. Then characterizing and better understanding the BCI user experience, notably using VR as a means of study. And of course, the third research axis is to design novel BCI-based interaction techniques for and in virtual reality or augmented reality. And the last one is the transfer of all our research results into novel immersive systems for various application purposes like medicine, health, sport, entertainment, etc. And I'll try to show you a lot of examples later on. And of course, by combining VR and BCI, it means combining complex technologies like EEG, but also fMRI, together with various kinds of 3D display like VR headsets or caves, augmented reality headsets, also combined with haptics or other means of interaction like gaze tracking, etc. And we like to conduct real-time and online experiments with participants who are more in the online kind of study and not offline processing of EEG data. So I'll try to show first some side projects. The first one is OpenVibe. It's a project, one of the standard software of the community, the BCI community, and there are lots of systems which are based on OpenVibe today. And we continue to develop this tool at INRIA. It's an open source, free software for brain-computer interface with lots of and it has established among the community, among the top 2 or top 3 software in the field. So feel free to use it, of course, for your application. It's free and it's quite practical to use. And here at INRIA, we are maintaining this software on a long term, and we really want to make this and to establish this as a very current tool, something which is here for, we hope, for years. We have just released the Circus version, the Circus release of OpenVibe last month. There are lots of users, you see some figures here, 1,000 users are now following, and it corresponds globally, this OpenVibe software, to 14-year man of development, so it's a lot of effort to pushing this tool, but we believe it's very important to provide tools to the community to develop and conduct their research on this challenging topic. Some examples of systems or applications based on OpenVibe here. If you type OpenVibe on YouTube, you'll find lots of examples ranging from artistic creation to motor studies or psychological or neuroscience studies, robotic control, on video games, etc. There are lots of examples if you want to have a look. Then later on, we had this really great project on brain-computer interface and video games. We were quite the first targeting this together with Netherlands, a great Netherlands project also at this period, to target this field of application. We did that with main actors of the field like Ubisoft in France, and we designed several proof of concept of video games controlled by EG data. You see here some examples here on the videos on the slide. I hope that you can see the video. On the bottom left, it's a Space Invader-like shooting game where the virtual spaceship is controlled by the visual cortex and SSVP, the visual evoked potential, and you have to concentrate on different areas of the ship to control the displacement and the shooting made by the ship. And on the right, it's another very interesting situation. It's one of the first multi-user BCI-based video game where two users are facing one against the other using their brain. It's a mental duel where they have to imagine left or right hand movements from sending the ball to the right or to the left in competitive mode. And some illustrative results now about the different research axes that I mentioned. Regarding the first one, characterizing neuromarker, this is a great example in this video of a paper that we published a couple of years ago at VR, where we show how we can elicit some great neuromarkers of disruption of agency and issues with the control of your virtual body. So imagine you are immersed into an avatar, a virtual body, and your virtual body starts to behave a bit strangely. For instance, due to tracking issue, your virtual arm is moving strangely. And we've shown that some neuromarkers can be elicited in the brain, which could enable to detect this situation directly in your brain and potentially correct them. Another application interesting for this aspect is sport training. You see here another video in our Immersia room where we have a training scenario for the Olympic shooting, the 10-meter pistol Olympic shooting sport. And you can train here in virtual reality with opponents and with a challenging audience in your back. And we can here look at the neuromarker in the brain of the shooter, which can characterize a good shooting versus a bad shooting in order to better train the athlete in the future using neurofeedback, as Felix was explaining a little bit earlier. We were quite interested in trying to characterizing the BCI user experience, for instance, investigating the frustration of the user, and also his or her cognitive load. It's nice paper. I want to have a look at them, showing that, for instance, surprisingly, the frustration of BCI user is unexpectedly low compared to traditional interface. And also with some BCI paradigm, we surprisingly showed also that it's the cognitive load is not that high, actually, especially with SSVP and evoked potential. You can actually do something else at the same time of using the BCI. You can think of something else. An example of our this research topic dedicated to BCI-based interaction techniques, and here it's a line of research which is quite interesting. It's a hybrid system which are mixing BCI with other inputs and other devices. Here it's a paper, but more generally we could think of other kinds of combination. But in this paper, we combine gaze tracking and gaze inputs together with EEG inputs and brain inputs in order to improve the selection of targets in the menu. And we developed and we designed a probabilistic approach to fuse to a fusion method for merging gaze input and EEG inputs into the same pipeline to improve the selection of targets. But in the end, we've shown that the gaze alone is very efficient already, and the EEG plus gaze remains, of course, better than EEG alone. Here, I will not enter into too many details on this one because Hakim is going to present this in more detail, but I'm teasing his presentation. as it is his PhD work on BCI-based interaction techniques and 3D user interface for the robot control of augmented reality with the HoloLens. It's a great PhD work, and Hakim will reply this, but it's a great topic of research. Those 3D user interfaces better incorporating BCI and EG inputs in augmented reality. On this combination of technologies, I think we were one of the first also to connect the brain-computer interfaces with another great technologies that we like to study in the lab, haptic systems, haptic interfaces, like this force feedback arm. And in this really great paper, we had a lot of fun in connecting here this force feedback device with the brain of the user. And the idea here was to activate force feedback and guidance in this labyrinth, in this maze, in this maze, we can activate force feedback for helping the user and guiding the user when the cognitive load is detected to be high, which corresponds to the changing color of the cursor here, which is changing to blue when the cognitive load is quite high. I suppose in the video here it's quite difficult to see this, but we can refer to the paper if you're interested by this aspect. And later on, we did a proof of concept quite similar it's a quite similar idea here. It's a medical simulator which is dedicated to medical doctors to train to a biopsy using haptic feedback and visual cues. And here, similarly, you can activate the cues when the cognitive load is high, when the mental workload is high, as detected by the EEG systems and by the brain computer. To go one step further in the connection between BCI and augmented reality, we indeed designed this mind mirror that Felix already introduced in his presentation, where you can look at your own brain in action in your head in mirror mode. It's a very fun and very teasing system where you can look at your brain and try to activate this or this area of your brain, and this or this activity in your brain activity. And this indeed is dedicated to neurofeedback. So this capacity of the brain and of the user to take control over some brain activity and to take control over his brain patterns. And we are now pushing it a little bit further with this combination of EEG and fMRI. It's a quite unique setup. It took us a bit more than 3 years. I'm launching the video here so you see it in action. It's one of the, I think there are 2 or 3 systems like this in the world. It's a real-time EEG plus fMRI system. So the participant is equipped with the EEG handset, and then he enters the fMRI, and then we can sense and measure both EEG and fMRI inputs in order to increase the neurofeedback, the training of the brain. Here it's motor activity and motor imagery. And I can activate the second video here where you see the task of the participant. The task of the participant is to reach this blue region with the ball, to make the little cursor go up to the blue region here. And to do that, he has to activate both EEG and fMRI neuromarkers. And you see the fMRI results at the bottom of the slide here. You see that with both systems, EEG and fMRI, you activate a bit more with the brain than using only EEG or only fMRI. So it's very promising for neurofeedback application. And in our case, it is applied now to stroke rehabilitation. Voilà. So this concludes more or less my talk. I can say a few words about what we envision as the next steps. So for us, it's a moment when and where technologies are converging, and we hope that in the future we will see more native hybrid technologies mixing more integrated virtual reality and neural imagery capacities, such as here in this example, the Neurable headset, which is natively proposing dry electrodes together with a VR headset. And we envision also lots of applications for health, sport, training, education, games, as was a little bit teased in my presentation. And I can finish with this great and funny last demo that we did in our team. It was a couple of years ago, but we connected our Immersia room to an EEG headset, a wireless EEG headset, and we have designed this Star Wars inspired demo. It's a virtual Dagobah. It's a planet where the Master Yoda is training Luke in the famous movie, and you can train here to lift by the force of your brain a virtual spaceship. Scale 1 in our cave. It's probably one of the most fun demos that we have in our group at the moment, which is connecting also and a lot of different technology. Okay, this concludes my talk. I'd like to thank you for your attention, and if you have questions, I'll be happy to answer that via Hakim's microphone again.
Thank you.
Thank you.
Questions, please.
Maybe my presentation was super clear, or on the contrary, my audio was so crappy, but it's okay. We can also move to another presentation.
I think maybe people are shy in using the technology here. I have one short question if nobody else has one. So what is your take on mobile XR applications? So we saw a lot of very impressive examples, but most of these were still lab-based. So what do you think? Will we at some point get out of the lab and use the systems outside, or do you think that's impossible or not interesting? What's your take on that?
Wow, I'm not completely aware about all the examples that you have in mind, so I'd be happy to talk with you a little bit more about these great examples that you are mentioning. But you are talking about wearable systems that would combine EEG headset together with AR headset and enabling outdoor applications. That's what you are talking about?
Yeah, so once you, for example, have to rely on the computational power you can take with you.
I'm not sure I'm super qualified to answer this one, but it's really relying on the manufacturers of the systems to tell us if it's sufficiently compact to enable a wide autonomy. But in terms of proof of concept, I think there are lots of things that we can work on. Hakim is going to display a lot of great potential applications that he has developed on combining AR and AR headset together with EEG inputs. And clearly there are lots of potential applications in sports, in maintenance, in education. So it's very promising. I think it's if indeed the headsets succeed in going one step further, it will be very convenient for those applications. But I don't know if I can say more about this.
Yeah, right. Thanks. So there was another question. I think Birgit wanted to ask a question.
Yes, I have a question.
Yeah, shoot, please.
Hear me?
Yes.
Do you hear me? Okay, great. Thank you for this really nice and clear presentation. I was wondering regarding that experiment where you do combine BCI with EEG and fMRI, how you deal with artifacts from the fMRI.
Yeah, it's a big challenge. Thank you for the question. It's part of the challenge. to remove the artifact coming from the fMRI in the EEG data. So we are using actually a commercial package sold by a company which is proposing to remove a lot of artifacts from the coming from the fMRI and the EEG. So it's a special system. It's a EEG headset which is compatible with the fMRI and which is coming with a set of toolkits to do that. In addition, on our own, we have also additional filtering and signal processing techniques in the EEG for deleting and cancelling other artifacts. But it's a big challenge in the fMRI. Still, what we are looking at the moment, we have some background now about these experiments after 4 or 5 years of research on this. And clearly the EEG signals that we have are a little bit less performant than the one that we have outside the fMRI, but we can definitely use them for our neurofeedback, our bimodal EEG and fMRI neurofeedback, and it's still working and it's still enabling to do neurofeedback. Our first results with stroke patients are quite promising. We have not published yet on this, but it's coming. And it's very encouraging.
Cool, thanks a lot.
All right, so I don't see any further questions. So I think we move to the next presentation. So our next planned speaker, Lisa, has issues joining or rejoining this room. So there seems to be some technical trouble with the application, but Hakim, you said you're ready to present next, and I think that really ties nicely to the teaser which we already got from Anatol. So Hakim, you can fire up your presentation. That's so.
Yep. So hi again. Hello, everyone. I hope you hear me well. And sorry again for the special solution of using the phone for Anatol's talk. My name is Hakim Si Mohamed. I am associate professor at University of Lille in France. And previous to that, I conducted my PhD thesis under the supervision of Anatol in Rennes. So I'm going to talk a bit more in details about what I have been doing during my PhD thesis. To start with, what actually has motivated us into work on BCI, at least for when I decided to switch my thesis towards this subject, is that the idea of communicating and interacting with virtual environments through thoughts is a very widespread fantasy. Whether it is on movies like The Matrix or X-Men that we all know about, this is something very recurring into the popular culture. But still, the question remains of how is it possible today with the tools that we have at our disposal? How is it possible to interact with these virtual and real elements through the brain activity at once or in different conditions? Well, one idea of trying to meet this objective was to trying to combine brain-computer interfaces and augmented reality, because on the first hand, brain-computer interfaces hold this promise of being able to connect a brain and a computer, where people would, in theory, be able to interact and use a computer or manipulate any system only with their brain activity, through modulating their brain activity, their cerebral activity. And in the other hand, augmented reality enables the integration of virtual content into the real world here, and thus enabling this idea of combining real and virtual elements that we wanted to interact with using brain-computer interfaces. And the combination of these two offers a lot of applications in different domain. Like we can imagine how we could use brain-computer interfaces and AR to interact with robots, which I'm going to talk a bit later, or for health application like Anatol presented, or even for entertainment, which is a very popular subject, but did not used to be that much a couple of years ago, where we want to build new applications where the idea is to entertain or video games using brain-computer interfaces and AR. And more specifically, the research questions that we wanted to tackle in order to be able to achieve this combination of AR and BCI was first, what kind of brain activity can be used in AR? Like Felix and Anatole mentioned before, there are a lot of BCI paradigm, a lot of type of brain activity that one can use in order to interact with this system. So what or which one of those, or to what extent can we use this type of brain activity into AR? What is compatible with augmented reality in terms of hardware, in terms of application scenario, in terms of graphical user interfaces, and so on? Then how can we improve the AR graphical user interfaces in order to work with reactive BCI? Because one important component of a brain interaction, brain-computer interaction system is the fact of having graphical user interfaces that enable the user to modulate his brain activity through focusing. For instance, with the SSVP focusing on flickering targets, or the P300 when you focus on letters flickering on a keyboard. So how do we design graphical user interfaces that are at the same time intuitive for the users and still elicit high enough potentials in order to be detected through the BCI? And then lastly, how can we take these combination a little step further into building new interactive systems that exploit the brain-computer interfaces in the scope of augmented reality? So in order to try at least to answer some of these questions, for example, we have decided we have had the occasion to try several, or to study several BCI paradigm in the scope of augmented reality. The first one was the steady-state visual evoked potential, which is based on, as Anatole mentioned, the fact of focusing on flickering targets in order to send a command. So we were among the first to try and see whether in the scope of a optical see-through augmented reality, it was still possible to elicit SSVP responses. So we conducted an experiment where people had to perform a series of SSVP tasks, even in the scope of motion, because we know that one of the biggest advantages of augmented reality is the possibility to move and to have hands-free while interacting. So we studied whether it is possible to use SSVP in AR while the user remains still, or with different levels of head motion. Interestingly, and in line with our hypothesis, what we found is that there was a clear decrease of the classification accuracy of SSVP responses with the augmentation of the amplitude and thus the intensity of movement in the experiment. But interestingly, what we noticed as well is that there was no, at least not a strongly significant difference between no movement and 40 degrees of amplitude movement, which suggests that still at some point it is possible to, let's say, have low amplitude movements while still being able to detect the SSVP responses. A second paradigm that we wanted to use more recently was the error potential. So basically, the error potentials is also called the oh shit signal, and basically it happens in the frontal-central region of the brain when a user notices that an error has been made. So our idea was to try to see whether it was possible to detect these error potentials when the user were facing commonly happening errors in augmented reality. Namely, we designed an experiment where the idea was to perform a center-out task with 3 types of shapes that the user had to drop into the corresponding shape: the cylinder for the circle, square for the parallelopiped, and the tetrahedra for the triangle. And we introduced some types of errors. For example, here in the second video, you can see that the tracking of the object the user is manipulating is lost, and the object gets frozen in mid-air, which corresponds to a tracking error in augmented reality. We also have the feedback error, where the user drops the correct object into the correct shape, but still gets some negative feedback, and the shape turns turns red. And the last type of error was a background anomaly. So we wanted to see whether a task, an error happening in the rendering of the scene. Here we can see this frame that flips and gets into an unrealistic position on the table. When that happens, does it elicit error potential, and do the users notice it, and is it possible to detect error potentials when this type of errors unrelated to the task happens? So you can notice that here I'm talking about augmented reality, but the experiment was conducted in VR, because what we wanted to have a more controlled experiment, but the idea was to simulate some errors happening in augmented reality, and we think that the results may be translated pretty easily. And interestingly, what we found out is that at least for the tracking errors, there seemed to be a strong response here. You can see here in the frontal region, a strong negativity followed by the positivity, and which is a very characteristic to the shape of error-related potentials into the brain activity of the people, and that we could even detect those into signal trial with a classification accuracy around 85%, which suggests that for this type of strong or highly impacting errors like tracking errors, it is possible to elicit and to detect these tracking errors from the EEG data of the subjects. I will not go much further into detail, but we can discuss if you have questions later. But we also noticed not that high amplitude error happening with the feedback error, but the background anomaly did not seem to generate or to elicit any error potential. But we cannot jump into conclusion right yet, because we don't know whether the user noticed the error or whether it was the impact of the error that had an issue. But that's an interesting point to talk about. Then later, we decided also, still continuing with the SSVP paradigm, to study how it is possible to display, or how it is possible to introduce a display strategies, or how to display the flickering targets into an augmented reality system, so that it is intuitive, meaning that the user understands pretty quickly what target corresponds to what command, but at the same time to be effective enough. So we introduced a display strategy of 5 dimensions of how it's possible to display these flickering targets in the scope of controlling a mobile robot, a 2D mobile robot. So the display strategies were whether the targets were put frontally to the user, whether it would be centered on the field of view of the user. But here you can see in the video that we obtained 32 different display strategies that you can see. Well, I hope nobody has epilepsy here in the room because the video, but that's still the video I think is not so great quality. Anyway, so we can see that some display strategies were really different on how the targets would rotate with the rotation of the robot, whether it would be fixated on the robot or the user's center of the field of view. And fortunately, we detected that only 2 dimensions out of these 5 had actually a significant impact on how coherent and intuitive the users perceive the interface. So we went further and decided to try to evaluate what was the impact of the display strategy. So is it important, or does it have an impact on the actual classification accuracy of the signal, or the display strategy of the targets? So we designed an experiment where the users had to move a virtual robot on the ground, but the targets were differently displayed depending on the 2 dimensions. So here we had every represent. So each video here, or each display strategy, is the best video or the best display strategies of each one of the 4 groups that were obtained with the 2 dimensions, the 2 binary dimensions. Interestingly, what we noticed here is that there were a significant impact of the display strategies on the classification accuracy, but mainly regarding the size of the targets. And interestingly, what we've noticed also is that there were no significant difference between the classical display strategy, which consists on displaying the targets on the center of the field of view of the users, and the one that was noticed as or rated as the most intuitive with the users, hence suggesting that there is a very interesting trade-off to find between how intuitive and graphical interface is with how well or how strong the BCI response is elicited. And so in the end, what we wanted to try was to aggregate all these results into a functional prototype of controlling a mobile robot. Here the user had only through using SSVP could focus on one of the targets in order to move the robot from in this predefined shape. And our results were really encouraging. Here you can see that the robot was moving pretty slowly for 2 reasons. First, because we did not want it to crash if anything went wrong, but also using the same speed of rotation and of movement that we noticed from the experiment where we studied the impact of head movements on the classification accuracy. And this was really encouraging into pursuing further, and we wanted to explore new interactive systems using SSVP and BCI. And we conducted now another study in collaboration with a tech company in France, which is the Orange Group, where they actually came to us and wanted to explore the feasibility
everyone.
of introducing augmented reality and BCI in order to interact with a smart home environment. So here we developed a prototype where the user actually could manipulate different home appliances using SSVP. Here we can notice that when the user moves his head, depending on what type of objects are in his field of view, the user has different flickering targets appearing in his field of view, or flickering at different frequencies. And then when focusing on one of them, we had binary command objects that only directly specifies a command to send the robot, like an on-off operation. But we also wanted to go further and see how it was possible to use this strategy in order to interact with a much more complex object, here represented by the television, for example. So is it possible to have a hierarchical menu in order to have several commands? One of the limitations that we had here, or one of the constraints that we had, is that we only had limited number of targets that we could display to the users at once. Hence the idea of using a hierarchical menu where the user could first turn on the TV, and then when selected the TV again, he could like change the channel, or go back, or change the volume. And as a conclusion with the title of the talk and to leave some room for discussion, the whole purpose of this workshop was to study the opportunities and the challenges raised by combining BCI and AR. So in terms of opportunities, as Felix has mentioned before, it is very interesting to notice this duality and how these two technologies can benefit each other. First, we have noticed that, for instance, augmented reality can provide a BCI with the integrated graphical user interfaces that enables not only to interact with a computer screen, but also with real objects through the augmented reality interface, and the flickering targets, or the stimuli, or any kind of stimuli that the user needs in order to generate or to stimulate his brain activity. We also talked about the mind mirror and how augmented reality could be a very promising source of feedback on how the brain activity is perceived, which is a very important notion of being able to interact with the BCI, to know exactly how, or am I doing the task correctly? Because when you press a button, you have 100% chance of knowing that, okay, you have pressed it very well, because you have this tactile and haptic feedback of pressing. But when you try to modulate your brain activity, it's very difficult to know whether you're doing correctly, and that helps in order to send or to improve how well you interact with the BCI. And integrating this feedback into the real world may be a very interesting opportunity. You know, on the other hand, we talked about the fact that BCI also provides a new hands-free interaction media. Well, we can discuss about how well it performs, but in fact, in several scenarios, it offers new means of interacting with the real and virtual environments without having to use their hands only through the brain activity and to different paradigms. But I would say very importantly and very interesting opportunity is that BCI today represents a very valuable source of information about the user's mental state, or what we call passive BCIs. And there are a lot of works conducted today on trying to find different neural markers related, for instance, with different sense of user experience into VR and AR, the sense of embodiment, like agency and body ownership, etc. And it raises a lot of opportunities in terms of using the brain activity in order to detect how the user, or what is the mental state of the user, in a way that is maybe difficult to get otherwise. But facing all these opportunities, from the main challenges, and this is just a tentative list of challenges, we can still discuss them later. I think some of the main difficulties of when it comes to combining BCI and XR in general is, first, of course, the classification accuracy. For many paradigms, we are very far from reaching a 100% or even a 99.99% of accuracy that a keyboard or mouse may have, for instance. But for some contexts, it might still prove valuable to use a BCI. And another difficulty is the cumbersomeness of the recording devices, because it's very difficult to imagine today having to wear for instance, a wet electrode headset in order to interact in augmented reality. So there is this need of designing new electrode technologies, or maybe even to mix between augmented and virtual reality headset and electrodes in order to have off-the-shelf systems that work and enable to detect the paradigms. And another challenge is the sensitivity of the signals. many times it actually may be tempting, for instance, to use artifacts in order to work with BCI. But the reason is the signal is very noisy to different source of artifacts like muscle noise or the electricity generated from muscle activity. So it is a very challenging issue of always trying to make sure that what is actually detected is related to brain activity and not artifacts. So that adds another layer of complexity when trying to combine VR and BCI. And lastly, but this is very inherent to the BCI field, we have this intersubject variability, which makes some people very keen to use a BCI and very skilled at doing so, but other people require maybe long sessions of training, but also the same, sometimes some algorithms work very well to classify the BCI paradigms for some people, but the same would not work. So there is a necessity of training both in terms of machine learning, in terms of training how to detect the signals, but also in terms of user training on how to use a BCI. And of course, I would be happy to talk more with you regarding these issues. And this concludes my talk. I would like also to thank you for your attention. And if you have questions, I will be very happy to take them. Thank you.
Thank you. Questions, please.
I'm also reading the chat. If you prefer to type questions, but as Anatol mentioned, maybe the talk was just very clear, or maybe for any reason it was not that much.
May I ask one question? How well can you discriminate? So you mentioned your work on the error detection, right? So how well can you discriminate different types of errors? So do you mostly find something was wrong, or are you able to discriminate between different errors which occurred reliably?
Well, thank you, Felix, for the question. It's actually a very interesting one that we also had ourselves. So I think I would give you a twofold answer. The first one is regarding the literature, when there is basically a lot of work suggesting that different types of errors, namely feedback errors, interaction errors, outcome errors, observation errors, so the different types of errors elicit different types of error-related potentials, at least, but this is still a matter to debate, at least in terms of latency and in terms of amplitude, and that would be related, for instance, to the impact of the error or how much the user was involved. In our case, so regarding the different types of errors that we studied, at least we did detect a clear ERP pattern regarding the tracking error, but it would be very it would be an overclaim to say that we have any different shapes or different error types of error potential regarding the different errors. But this is something still very interesting to study, whether different types of error or different impact of error trigger different shapes of error potentials. At least in the literature of HCI, this has at least been suggested to be the case. But for our study, we only focused on whether we could, as a first step, detect them or not.
Thanks. Any other questions? Last chance.
Hello. Hello, can you hear me?
Yep. Yes. Hi.
Very nice presentation. I have a quick question. So, in the hands-free application of the BCI, when you say like BCI controls the AR visualization, so what component of BCI are you talking about? As in, like, because there are like a lot of bands and band power and other features from the EEG. So, what specifically do you usually consider as like a trigger, or let's say like a way to which you consider to control the visualization?
Well, thank you very much for your question. And actually, that's definitely true. But it's related to the notion of paradigm, or at least that's the term that the BCI community used to employ in order to talk about the different types of brain activity or the neuromarkers that are exploited in order to interact. So when you mentioned the band powers, I may, for instance, suggest or think about motor imagery, where you can detect whether a user is trying to move his right hand versus his left hand using the mu and beta band into in the motor cortex. The issue here is it's still difficult, and you can only detect whether the user is trying to move right versus left, but you cannot have a fine control on what kind of brain activity can be used. So this is one of the first research questions that I mentioned here, about trying to figure out what kind of brain activity can be used in order to interact in AR. There have been works suggesting that we can use, for instance, motor imagery in VR. It works pretty well. Here we have focused on passive and reactive BCI, so we have shown that it's possible to use SSVEP, so the response to a focus on a flickering target, or the ERPs. But I also know that the P300, for instance, has also been studied into. So there are a lot of different brain activities or BCI paradigm, all related to different neuromarkers that can be exploited in AR and VR, but there is no free lunch. So it's always necessary to study each brain paradigm that we want to use in the scope of the application that you want to do. I hope that answers the question.
Thank you very much. Yeah, thank you very much.
All right. So we are still missing our actually second speaker, Lisa, but she's still trying to, she's switching to another computer. So what I suggest is, as we're also running a bit late, that we do a short break now, maybe 10 minutes, and then after that we'll either continue with Lisa's presentation, or we'll continue with the next one with Bridget. Is that okay with everybody? Any comments?
Seems fine to me.
All right, then we'll have a short break, and then we'll do 10 minutes, and in 10 minutes we'll be back here. So either stay in the room and interact if you want, or take a short break from your VR experience. See you in a few minutes.
Welcome to the iLearn Virtual Campus. Welcome to the iLearn Virtual Campus. Please sign up for a free iLearn membership on our website. Check out our 7th annual conference coming next spring 2021, and let us know if you're interested in hosting events or leasing space on our campus by emailing campus@immersivelrn.org.
Good afternoon, and
Anything new, Lisa?
Good afternoon and welcome to this talk. My name is Birgit Niru.
恒宇是吗？恒宇 with a C.
Hello.
Okay. Hello, everyone. I don't think Lisa has fixed her. Maybe you can.
Yes. Do you hear me?
Okay. Awesome.
Yeah, okay,
So
good.
yeah, thank you again, everyone, for being here. I'm very pleased to introduce Brigitte Nierula, who is a postdoctoral researcher at the Max Planck Institute for Cognitive and Brain Sciences. And previous to that, she was working with Professor Raves Sanchez Vives, and she's going to present some of her results today. Thanks. The stage is yours.
Thank you. So my video was pre-recorded, or my whole presentation was pre-recorded, so maybe one can start it. I was worried about connection problems. Relevant from an ethical point of view, but it is also very relevant when using BCI for neurorehabilitation. Before going further, I would like to give you some background on body ownership, agency, responsibility, and brain-computer interfaces. So how do we know that a certain body is our body and not the body of another person? Referring a body to oneself has been shown to rely on correlations between visual and tactile stimuli and/or between visual and motor commands. A classic experiment named the rubber hand illusion can demonstrate this. It not only is possible to induce a body ownership illusion over body parts as you have just seen, Petkova et al. Have shown in 2008 that one can also induce body ownership illusions over the whole body. And it is possible to induce body ownership over a virtual body. A series of studies from the lab of Mel Slater and Maria Sanchez-Vives showed that in virtual reality, it is also possible to induce body ownership over a virtual arm through visual tactile stimulation, similar to the rubber hand illusion, and through visual motor contingencies. And it is further possible to induce full body ownership over a virtual body. Interestingly, Perez Marcos et al. Found that if we control the movement of a virtual arm by means of a brain-computer interface, in this case, they used the motor imagery paradigm in order to open and close a virtual hand by thinking. This would also induce a virtual ownership illusion. On the top, you can see the setup of the experiment, and on the bottom, they have shown, there's a graph that shows the relationship that they found between the subjective illusion of ownership that participants reported and an objective measure of the illusion. In this case, the measure was by EMG. So how do we know that this body is our body and not the one of another person? We have seen a series of experiments showing that when multisensory input correlates, our brain infers body ownership. This means that our internal body representation is dependent on multisensory correlation and is not fixed. This also means that we can induce body ownership through multisensory and visual motor correlations. This way, external objects and also virtual objects can be experienced as if they were part of our own body. So now we've learned about body ownership, but what about agency? How do we know that a certain movement is our movement so that we can feel responsible for its effects in the environment? The sense of agency is the attribution of an action to the self. It is the feeling that we are the agents of our own movements, which gives us a sense of control and responsibility over our own actions. Body ownership and agency are closely linked. In order to feel agency over one's own actions, one needs to have a certain sense of body ownership for the own body. Agency has been explained in the frame of motor planning and execution as the result of a matching between the predicted and the actual sensory feedback. So the idea is that when we are planning a motor action, our brain predicts sensory feedback before we perform the movement and then compares the prediction with the actual feedback. If there is a match, this results in the feeling that this was our action, meaning the feeling of agency. This is a process that involves motor areas. But can we also experience agency over actions we did not perform? Wegener et al. Showed in 2004 that it is also possible to perceive agency over another agent's movements without moving one's own body, just because the arms of that other agents are in a feasible position. And in a study by Banaku et al. In 2014, they showed that when participants have a strong feeling of body ownership over a virtual body, it is possible to attribute the spoken words of that body to oneself, even when not having spoken. So there is not always a motor preparation taking place when there is agency. Therefore, we address the question to what extent activity in sensory motor areas is critical for the sense of agency. There are further examples in which brain activity is not directly controlling a body movement, but indirectly through a brain-computer interface. A brain-computer interface, or BCI, is basically a feedback loop in which the brain signal is processed online and transformed into an output signal that can be sent to any device, for example, a prosthesis, a wheelchair, or like in our case, a virtual body. And the device sends then feedback back to the user. There are different protocols of such BCIs. Among others, some exploit the activity of sensory motor areas and others activity of visual areas. In protocols that exploit activity of sensory motor areas, the participant's task is to imagine a movement which can then be detected by the BCI system. In BCI's protocols that exploit activity in visual areas, the participant's task is to look at a flickering light with a specific frequency, which can then be detected by the BCI system from primary visual areas. In this study, we use both of these BCI protocols. Specifically, we were interested whether BCI can induce agency and whether induced agency levels are different if the BCI is based on sensory motor areas compared to visual areas. So taking together, our research questions were, is there agency over movement induced through BCI? How relevant is the cortical area activated for the initiation of the movement? Which paradigm of BCI used for motor control is better at inducing agency? And can BCI also induce feelings of responsibility with respect to the results of an action? To answer these questions, we designed an experiment in which participants were sitting with their hands resting on a table. They were wearing a 59-channel EEG and a head-mounted display through which they could see the virtual environment, in which they saw a virtual body from a first-person perspective, which was co-located with their real body. Here you can see the participants' view of the virtual environment and the arms of the virtual body. In front of the participants, there were two virtual buttons that were blinking. Each trial started, as you can see on the bottom left, with a fixation cross. Then an arrow in the middle indicated which one of the lights participants should move the arm to. And then the virtual arm movement came. However, we told participants not to move their real arms. Instead, they should move the virtual arm through a brain-computer interface. There were three different conditions. Participants either induced the virtual arm movement through imagining the exact same movement, or through looking at the blinking button that the arm should move towards. And in a third condition, they simply observed the arm moving. This was a control condition, and they were not able to have any control over that movement. They could just observe it. Several times throughout the experiment, we were asking participants how strong they felt it was them controlling the virtual arm movement. In some trials, the virtual arm threw by accident an object off the table. I will show you one of those trials now, and the beginning of the trial was always the same, also in other trials where there was no object falling off the table. Just the end where the object falls off the table differs from a normal trial. And in this case, there was an object accidentally thrown off the table, and afterwards we asked participants how strong they felt responsible for breaking this virtual. Our results showed that participants perceived highest levels of agency during the motor imagery condition. SSVEP, so the visual condition, came second and observed third. Interestingly, participants perceived only high levels of responsibility during the motor imagery condition. SSVEP did statistically not differ from the observed condition. And the same pattern was visible for body ownership. So only for the motor imagery condition, there was a statistically different or statistically higher, participants reported a statistically higher level than in the other two conditions. Next, we looked at the brain activity in sensory motor areas in the three conditions by extracting the event-related desynchronization of the alpha rhythm. On on the here you can see the area where this rhythm was mostly present, the somatosensory areas, and here is a graph of the brain activity in these areas. And on the y-axis, you can see the event-related desynchronization averaged over all participants. And since this is a desynchronization, lower numbers indicate a higher brain activity. So this graph basically shows that during the preparation phase, which starts at 0, which is the phase before participants saw the virtual movement, our manipulation worked also on a brain activity level. You can see that as expected, during the motor imagery condition, we have more activity in sensory motor areas than during the other two conditions, which have similar levels to the baseline. Next, we correlated the event-related desynchronization during this phase with participants' ratings of responsibility and control, and found that for responsibility, there's a relationship with event-related with brain activity. So the higher the brain activity, the more participants are feeling responsible for breaking the virtual object. Coming back to the situation described by Taidoni et al., where a person in Rome controls a robot in Tsukuba, we can conclude, based on the findings from our study, that people can experience agency over a surrogate body, in this case, a robotic body, controlled by a BCI. However, the BCI paradigm matters. BCI control by the activation of sensory motor areas induces higher control and responsibility. This is very relevant. Oh, sorry, I forgot. This is very relevant for neurorehabilitation and has ethical implications. Thank you for listening, and I want to give special thanks to Maria Sanchez-Vives and Mel Slater. And in their lab, the event lab in Barcelona, this study was conducted and planned. I want to also thank Vadim Nicolin, Mireia Borrell, Bernhard Spanglang, and Matteo Martini for their contributions to this study. Thank you. Paradigms, like from my experience, I would not know how combining, for example, SSVT and motor imagery could contribute to the feeling of agency and responsibility. But well, in the end, one needs to test this. But yeah, this is my feeling.
Thank you. Thank you for your answer. Any questions, guys? Well, then, thank you again, Brigitte. I think we can proceed in order to catch up with the schedule. So our next speaker is Athanasios Vouvopoulos Thanos. He is a research fellow at the Institute for Systems and Robotics in the Superior Technical Institute in the University of Lisboa. And I think the video is pre-recorded. By the way, I think he's facing as well a sound issue, so he will he's following the feed through YouTube, if I understand correctly, and then I will speak out the answers if there are questions. Is everything all right, Joe?
The cell death. There are two major types of stroke, which is the ischemic stroke, which basically is a blood clot kind of forming the narrow arteries and blood flow, and this is called a thrombosis. And this doesn't allow the flow of oxygen to the cells, and they die. The second is the hemorrhagic stroke, which is actually a blood vessel ruptures and blood accumulates in the tissue around the rupture. So this puts pressure on the brain and causes loss of blood to the surrounding areas. Unfortunately, stroke is the leading cause of adult disability worldwide, and around half of the stroke survivors suffer from permanent motor and cognitive impairments. This results, unfortunately, to upper limb disability, which is critical because it reduces the activities of daily living. I will mention here briefly some key aspects of motor recovery. Well, first of all, motor functionality can be recovered by cortical plasticity or neuroplasticity. Neuroplasticity is the brain's ability basically to reorganize itself by forming new neural connections. So it reorganizes through the structure, the function, and the connections of the brain. So this is really important during the rehabilitation phase to maximize neuroplasticity. Now, in order to achieve this, and especially in a lesioned brain, we need to find alternate access to the motor networks. And this can be achieved through the mirror neuron system, which is a set of neurons that are active both during the execution of a movement or the observation of the movement. So even the observation of a motor action can invoke similar activity as the execution of the physical execution itself. Now, three of the key aspects for the optimal rehabilitation is the treatment frequency and intensity, which correlates with actual recovery. The movement practice and repetition play a fundamental role in recovery. And finally, specificity of the rehabilitation training with respect to the deficit and required functional outcome has an impact into recovery. Now, we've seen that virtual reality have shown so far a very positive impact on applying these guidelines in stroke survivors. And also VR is able to effectively incorporate these guidelines, such as the intensity, the task frequency, the duration of the therapy, in a novel and low-cost approach in the stroke population. Moreover, with virtual reality, we can have fully controlled environments. We can have task-specific movement reiteration. We can have minimally supervised intensive training, individualized training, and of course, feedback for reward and motivation, adding extra motivation mechanisms into the training task. Now, one more important element that virtual reality can bring into the rehabilitation domain is the sense of embodiment and presence into a virtual environment. So by embodiment, we mean the corporal awareness, the ability for someone to sense the virtual body as their own, and also in terms of presence, to be convinced that they are present inside the virtual environment. So it's really important, these aspects, to be present into the training paradigm, because that will help not only create an ecologically valid training scenario, but also potentially help activating some mirror neuron system through the visualization of the physical body. Now, for most of patients, those with severe motor disability, they cannot actually benefit from this VR training tool. So the question now is how we can actually interface those with the worst prognostic into the VR training. The solution is the use of course, brain-computer interfaces. And BCIs can provide this alternative non-muscular channel for communication and control with VR. With BCIs, we can bypass the central nervous system, and it has been shown so far that the regulation of neurophysiological activity in a closed loop can facilitate motor learning, which potentially could lead to recovery. Now, one of the ways we can use BCI is through motor imagery. And motor imagery is the mental imagination of the movement, is the mental rehearsal of a movement. And it has been found that it has a similar cortical activation as the actual physical movement. So it's also important to highlight that repeated practice of motor imagery can actually induce changes in the brain. And finally, it has been shown that the BCI actually boosts motor imagery efficacy during the stroke recovery. So as you can imagine, motor imagery paradigm in BCI, it's really important aspect for stroke rehabilitation. Now I'm going to talk about how we can actually merge these motor imagery BCIs with virtual reality. Since we talked how we can show action observation of upper limb movement with virtual reality, and how we can actually engage similar motor systems through motor imagery in a motor imagery BCI paradigm. Now, in the beginning, in order to understand the impact of VR feedback in the motor imagery training, BCIs, we created a study where we had 3 conditions. The first one includes the introduction of a motor priming session, where the participant, we mapped the hands of the participant to the virtual environment, and they had to perform the task physically. After the physical task, they had to perform the same through motor imagery in VR. And as on the second condition, they had to perform exactly the same training without the motor priming. And in the third condition, which is the control condition, they had to perform the same motor imagery, but with abstract feedback. To assess this, we used 12 healthy participants, where they actually did all 3 conditions in a randomized order. In terms of EEG data, we can actually see a trend between all of the 3 conditions, and we have actually added a 4th condition, which is the evoked EEG activation during the motor execution. And that way we can see 2 things. First of all, how far the control condition is from the VR conditions in terms of EEG activation, and also how close the VR is with the actual motor movement. So here we have the data from alpha and beta bands, which are the most reactive EEG bands during motor imagery. Now, in terms of BCI performance, we see a similar trend with VR after motor priming to have better performance compared to the rest. We see again a trend, but we couldn't find any significant differences. In terms of the perceived workload, again, we see that the motor priming, the virtual reality condition after motor priming has increased demanding in terms of workload. We see there's a significant difference between the VR after motor priming with the control condition, and we see also in all cases a similar trend. So that actually shows that there is something there that is worth investigating further. Going a step further, we don't want only to engage similar EEG patterns as the motor execution, but we want also to engage the subject into the rehabilitation training by introducing new motivation and engagement mechanisms. To do this, we designed a new training task, which is called Neuro. It's a rowing game, which the feedback is again delivered to hand-mounted VR, showing the upper limbs in the first-person perspective. It delivers some multimodal feedback through, of course, visual through the head-mounted VR, spatial audio, and also haptic feedback. In addition, it's try to have it as ecologically valid as possible with a real-world scenario instead of abstract feedback. And we also introduce some motivational mechanism as scoring and different levels. So what we initially did was to test this paradigm with some healthy participants. And we actually compared their performance, their classification output with similar studies, other studies that they have used the same feature extraction and classification methods, but without the VR aspect. So we included these other studies from the literature, also including our own studies from the past without VR. And we actually kind of like meta-analysis, we found this significant difference between the two groups, which is the VR with Neuro and the non-VR group studies. So basically here, by only changing the feedback modality, which is the VR aspect, we could possibly increase classification performance only by that. Now we have seen so far that we can engage similar EEG activity during VR training with the actual motor execution. In terms of EEG, we've seen that we can actually increase somehow the overall BCI performance by introducing the VR feedback. So what is a natural step is to see what kind of brain areas are we indeed engaging by introducing this new training paradigm. To achieve this, we need to go deeper. So we used an fMRI scanner with, again, the same conditions and abstract feedback, motor imagery with abstract feedback, and also motor imagery, and of course, motor observation with a Neuro training task. We recruited 10 young adults, and also we added an additional 10 older adults in order to see this. There is also an age effect due to the fact that this training paradigm is going to be used by elderly stroke survivors. So we wanted to account for that. So we ended up with 20 participants inside the scanner performing this motor imagery and motor observation task. So in this figure, we can see the activated areas. With blue is the increased activation of Neuro compared to the Gratz paradigm, and with red is Gratz paradigm greater than Neuro. So what we can actually see, this is of course undergoing work, but what we currently have is an increased activation in multiple areas during the Neuro condition. Primarily, we see a lot of occipital activation, which is the back side of the brain, which is responsible for visual processing. So as you can imagine, through Neuro, you have a lot of visual stimulation happening through the motor observation. So all the occipital lobe is actually, it has a greater activation than Gratz. More importantly, we see an increased activation in the primary somatosensory cortex that is greater during Neuro condition than Gratz. And of course, we have many areas that they're related to the mirror neuron system, which is really important in our case. In terms of the age, we didn't find any differences between the two age groups, which is a really good finding, because it's also in line with prior research, and it shows us that these will not have an effect because our target demographic is actually elderly people with stroke lesions. So this is a very really nice first result. So moving forward, now I'm going to show you the clinical implementation of Neuro in a clinical setup with one stroke survivor. So for this pilot, stroke survivor in the chronic phase had been recruited, and the intervention protocol included an assessment with the clinical scales for upper limb disability. Next, he had an fMRI scan where he used motor imagery and motor observation with Neuro before the intervention. Then he had 4 weeks of BCI VR intervention using Neuro, the hospital. And then after the end of the intervention, he had been assessed again through the clinical scales for the motor impairment. And he had again one more fMRI scan with motor imagery using Neuro. Now, after 4 weeks, we had again a follow-up session where he had been assessed again clinical scales and fMRI. In terms of clinical scales, we can actually see an improvement pre and post intervention. And in terms of the minimally clinically important difference, which is a measure to see if this improvement is significant in terms of clinical scales, we see an improvement of 9 points, which is within this clinically important difference. So which means that the improvement of this patient is actually significant and has an impact in his life. And after the follow-up session, we measured again an increase in terms of the motor capabilities, although it was lower than during the intervention. Now, in terms of brain imaging, we can see that on the first scan before the BCI intervention, there is not any significant activation happening during motor imagery with Neuro inside the scanner. As after the intervention, in the post scan, we can see a clear activation happening over the motor and sensory motor cortices. So we can see that there might be an effect there from the BCI intervention that helped the patient into his motor imagery capabilities, that now it is reflected actually as a functional outcome through the fMRI. Now, this increase in activation is also reflected in the follow-up scan. So he retained actually this functional outcome even 1 month post the intervention. Now, what is really interesting here is the self-report of the motor imagery capability of the patient, which is a subjective measure. And in this case, before the intervention, he scored really low in terms of ability to imagine himself moving. As after assessing the patient after the intervention and in the follow-up, we see an increase in the self-report of the motor imagery ability. So this is an example of how the functional outcomes are reflected both in terms of brain imaging in the really low brain level up to the perceived ability of motor imagery. So this increased ability of motor imagery could potentially help also in terms of BCI training in the future. In terms of current work, we're actually merging the two modalities of the EEG and fMRI, and that way we can actually harness the benefits of the high temporal resolution of the EEG with the high spatial resolution of the fMRI. This is really useful for us because in the case of stroke survivors with the lesion brain, it is really important if we can actually model these activated areas as captured through the bolt signal of the fMRI to create EEG features that can be actually used in the BCI paradigm. So that way we're going to have individualized features based on the prognostic and the disability of the patient based on these brain imaging data. Well, this is not going to help us only in terms of understanding more about the brain and the neuroplastic changes, but it will help us also increase the usability and the accessibility of the BCI. Unfortunately, and due to COVID now, a lot of these research have been hindered due to lockdowns. So we had to readapt our protocols to start acquiring data under these circumstances. But slowly we're going to continue, and soon we're going to actually be able to show some results in this front. Now, last but not least, and since this is also an augmented reality conference, I just want to show you a side project that I have with some colleagues from the Netherlands and Norway, where we're actually using augmented reality glasses fitted with some EEG, some electrophysiological sensors, basically, where we can extract some EEG patterns. On top, you can see some alpha activation, and also some EOG and some acceleration data. And we see how we can actually use a form factor of augmented reality glasses to acquire some robust data that could potentially be used in a closed loop inside an AR or VR environment. Well, thank you very much for your attention. I will be happy to receive now any of your questions. And if there is not enough time, you can also drop me an email.
So, if I may ask one question, Thanos, and now you have to type it. But so, how would you go about really figuring out the impact of using the VR on, for example, your training paradigm? So, how close would you say are you to isolate? Okay, this is the effect that the VR has on the training, given that it's probably difficult to compare any VR condition to a non-VR condition. So what are your thoughts on comparing these two settings? We can also, I mean, you can also always ask questions in chat, right? So you have, I think we have right now we have 3 different channels, so you can write just here in the app. Some people already also have asked questions on Wooba. That has the benefit that we can also answer them later if you're interested. And as Hakim is currently doing, there's also a YouTube feed, and there are questions there.
Yeah, maybe Thanos can write the his answer on the chat, and people can chat with him on the questions. I think we still have like 1 minute left before the next speaker.
Yeah, I mean, we can also always do that, right? So answer the questions asynchronously.
Exactly. I think that would be best, and we're a bit short on schedule right now. So it is my pleasure to introduce our next speaker, Andy Wilson. He's a partner research manager at Microsoft Research, and he's going to talk today about the seeking form factors and interaction paradigms to consumer AR VR BCI.
Thanks, Hakim. Can you hear me?
Yes, we do.
Yep.
Wonderful. Yeah, so I'm Andy Wilson. I'm at Microsoft Research, and I'd like to talk today about some things that we're doing at MSR to look at consumer applications of BCI for AR and VR. This is really a virtual team. The column on the left are MSR researchers, Microsoft researchers that they're looking at this these days. It's kind of a part-time thing. There are no real experts in BCI. Really, the experts are interns, of which Hakeem was one 2 summers ago now. So we're bringing in external expertise to teach us how to do research in BCI, and that's been wonderful. So what is our view on BCI? And I really mean Microsoft Research. I'm not really saying a whole lot about Microsoft's view as a whole. So there are some preliminary thoughts here. And then, I think we started with this notion of thinking about, if you're going to have a headset on your head like this bulky HTC Vive Pro, why not make that, with even more sensors, with EEG sensors, right? And see what we can do with EEG and BCI. Now, as you guys know, there's many modalities available to us: ECOG, EEG, MEG, fMRI, fNIRS, and we are, looking right now at EEG. I think for reasons that are fairly obvious to this crowd. Basically, it seems like the thing that's going to be quickest to get us to interactive rates. So we all know about EEG advantages. We had good temporal resolution, safe and accessible, but it has low spatial resolution and low signal levels, poor SNR, and interferences with the muscle movements or muscle activations is a very real problem for able-bodied users. So this is the EEG cap that we've been using lately. So this is the 24-channel gel-based 500 hertz Bluetooth interface. It's a wonderful device. Now there are, of course, many commercially viable EEG devices, or maybe they are. We're not really sure, but there's definitely a lot of playing around now going on with form factor, and we think that that's important too. So I don't have direct experience with all of these devices here. But it just gives you an idea of kind of what people are doing these days. This is one that we do have direct experience with. This is called the smartphone. This uses saline wetted EEG electrodes and 11 channels, and it's otherwise a pair of headphones with a rather large clamping force. In-ear electrodes are also something that we're very interested in. It's very unobtrusive. There's little setup, and maybe less influence from some muscle activation, such as eye movements. The disadvantages, of course, is that you have fewer electrodes, and none of the spatial mapping that you might have with a multi-channel cap, and generally lower SNR. And so that's kind of an interesting question: is can we make these in-ear electrodes practical? Now, there are lots of other people looking at this too. There are lots of different variations of this, and so I think this is kind of an exciting development as long as we're talking about form factors. So we've built our own in-ear electrode, and I'll present a couple of results around that. Some very preliminary things. We use a reference electrode attached to the earlobe, and playing around with different ways to isolate the speakers from the sensor to minimize interference. So EEG features, of course, you guys all know these things. E300. These are the things that I think are viable today. Alpha, ERP, the oh shit moment, motor imagery, and of course steady state evoked potential, which we're going to focus on quite a bit. And you guys know this. Each dot here maybe blinks at some frequency. This is exactly the paradigm that Hakeem showed you in the visual domain. But then there's also work being done to show that this works in the audio domain. So the so-called audio SSEEP. And in this case, you can attend to one stimulus or another. So there's two different audio signals, and I think this is very exciting because this is shows that it's multimodal, and also is like a fairly direct observation of attention. And so this is something that I think is very fascinating, that you can do this kind of thing. The project goals really are to demonstrate the feasibility of EEG BCI for AR and VR, in particular able-bodied users, and really keep the company abreast of the main challenges in using EEG in the consumer device. We're looking at in-ear electrodes versus the cap, and then also looking at steady-state evoked potential as a viable paradigm for interaction. And again, looking at SSEP across multiple modalities, including auditory, haptic, and visual domains. And we're also interested in end-to-end real-time interactions. And of course, we're open to exploiting, deep learning and these kinds of techniques to perform the signal processing. So we're really looking at these three interacting factors, right? The EEG features that are available today, form factor is particularly important, and the kinds of interactions. And we think that we can, we can play around with all three of these degrees of freedom to find something that works. And this is very much aligned with some of the issues that Hakeem presented. So the projects that I'm going to run through very briefly, they're all very preliminary in nature. These are things that we've just done in the last couple of summers, and a little bit during the regular part of the year. But really, it's intern-driven work. So a lot of the work happens during the summer. And so I'm just going to walk through these various projects, and they take very kind of slices at that Venn diagram that I showed, at looking at various kinds of problems associated with that. So the first one is, the first question we had was, in-ear electrodes I think are very exciting, but do they really work, right? And I'm sure some of you have experience with that and can probably know much more than I do. We did a very preliminary experiment where we play a target cue on one side, on the right or the left, and play a 10-second stimuli, and then ask the subject to attend to one or the other. And we can perform these frequency these charts of magnitude to look at having the stimuli in the left ear or the right ear, and then also to switch that around and move it over to the other ear, and show that we're getting the audio steady state response. And just really quickly, what we're finding is that we know a much weaker response when we're talking about the ASSR as a ratio from a baseline. And this is just a plot of the various subjects we ran, and then the relative ratio comparing the cap to the ear. One thing that leaps out right away, of course, is that some subjects are much better than others. This is, a concept that people refer to as BCI literacy, which, when you think about it as a consumer device, is really kind of a worrisome thing, a worrisome phenomenon that's kind of unexplained and needs a lot more work to figure out what's going on. So, but there's still something here, right? There's still, the ratio is above 1, so there's something going on. So, right, so there's something here. I think I just said this. And we also compared some of what we found there to the 24-channel recordings, and this is I can go into this in more detail offline. Auditory and tactile is something we explore. The question is, what about haptics? And this is just doing a ASSR experiment in the auditory domain. But then also performing something very similar in the haptic or tactile domain, where we used a vibrotactile actuator, one on each wrist, and this actuator was taped to each wrist of the user, so that leaves the user's hands free for other things. And we play different frequencies. Basically, we try to perform create a stimuli that is basically the analog of the audio. And then this is kind of what we get. So we get a classification. This is a very simple kind of classifier, and we can consider the performance with just the audio domain, the tactile domain alone, and then also the mixed domain. And you would think that the fused or the mixed stimuli would be better, but in fact that's not necessarily the case here. So, but it's still there's some interesting things here. Again, lots of variation subject to subject. And yeah, so this is another basically the linear discriminants, three-way classification. Yeah, I'm going to skip through this. And so tactile attention task is more difficult, we find, than the auditory, and that's demonstrated in here in a few places. And people had a harder time sort of understanding or just really doing the task. Yeah, more subjects, a lot of variation across subjects. So one of the issues with this experiment is, if you've ever heard some of these audio SSEP experiments, the stimuli are actually quite annoying, right? They're quite obnoxious. I would play them for you right now, but I don't think it's going to come through on the audio in this setup. But trust me, it's quite annoying. And a lot of the subjects even complained about it, and the audio, the volumes were quite loud. And so the question is, can we do something that's a little more pleasant? And so we chose to move beyond sort of the sequence of tones and then just use sequences of music. And then the task was basically just to detect an oddball sequence from a series of harmonically compatible, I should say, renditions of a couple of tunes performed by different instruments. And so and the task was to spot this change. And so we also spatialized the signal. So when the different instruments were in a different location. And then this is kind of what the task looked like. And we used this 11-channel EEG signal from the smartphone device. And we used auditory attention decoding process, which is something that's in the literature. It's, as a way to reconstruct the signal, and then perform the classification, and then with I think, do we have 10 subjects here? Yeah, I think we have 10, and then so we're showing some classification that's looking reasonable. So we're finding a positive effect, and people can actually do this task. So we can acquire information about cognitive states from compact EEG devices without the full brain coverage. And for certain kinds of stimuli, we can use polyphonic music as the stimuli, and direct users' attention to a specific instrument. And using a stimulus reconstruction method, we can decode the music attention. And this is work that's currently in submission. Another dimension that's kind of similar is to look at the visual SSEP in VR, and this is work that Hakeem did when he was here. And the question is, can we make SSVEP less annoying? These kinds of displays, can be quite annoying, visually salient but annoying. And so what Hakeem played around with was changing the visual angle or the size of the object, and then also the contrast and the frequency of the stimuli. And so what we found was, using this is in VR, that really only size mattered in terms of the classification accuracy. Larger is better. And so we were disappointed a little bit to show that there was no nice, that reducing the contrast of the stimuli just does not. It has an impact on the classification results. So this is something that Anatol showed earlier. I think it's a very inspiring kind of idea. You probably can't see the blinking on the ship. Here it's interesting that the stimuli is kind of hidden in the ship. The player moves around, but Hakeem and a few of us were looking at the different ways that maybe we can pull out that similar kind of signal in a more natural motion. So this is a hummingbird animation, and we looked at SSVEP from those kinds of stimuli, and with very preliminary results, we're finding some very promising classification numbers. And so the idea would be that we could embed those kinds of stimuli in a much more natural way, like this. So So right, so the stimuli. Actually, I need to correct what I said earlier. The contrast did not make the SSVEP any more acceptable to subjects, but it still, I believe, worked. Actually, Hakeem can correct me on this. He's right in the room. So larger targets work better, but they are more annoying to people. And then the preliminary result is the moving targets give the same SSVEP or something like it and are much more pleasant to look at. And then finally, I want to talk about some more recent work where we looked at the possibility of making SSVEP online adaptive. And so we've already heard a little bit of talk about error-related potentials. And so this is a very unique signal that's very, I would say, in the world of BCI is pretty easy to detect, has a very unique signature and fairly reliable. And so what we looked at was the use of error-related potential to correct an SSVEP classifier and do that in an online way. And so this is kind of an interesting idea that might help in bringing BCI to broader populations. The idea being you put the cap on and it automatically calibrates. So right, so many we've done a lot. Everyone's done a lot of SSVEP work out there. There's usually a calibration process, and the idea is to use the ERP detector to detect whether the predicted SSVEP label that's presented to the user is correct. And we're relying on the fact that the ERP detector requires a 0 or short calibration process. So this is kind of what it looks like. We're looking at time of the what we did, and then this is the kind of the result that we arrived at with a few months' work. So this graph on the lower left is a little complex, but the top bluish purplish bar is basically the fully calibrated and fine-tuned, like basically what you would do if you weren't doing an adaptive scenario, but did a calibration for the subject, and then and then you can see the green line, the bright green line, approaches that as the system adapts, and so that's kind of a good initial result. So this is kind of what it looks like. What you're going to see here is there are 3 boxes, and the subject's going to be queued to attend to one of those 3, and then the system shows its result. Now that unfortunately the results are rendered in green, which it doesn't come out very well at all in this video. The little, by the way, the small thing at the top that's affixed to the display is our sort of like kludgy way to synchronize the display with the rest of the system. So it's just a photodiode attached to a block of white. So there's no real adaptation here that I'm demonstrating in this particular video. It's really just showing the ultimate performance. So so the adaptive framework, initially in this very simple example seems to work. It improves the performance. Now I think we need a lot more data and more participants. We're like everybody else, we're caught out by the COVID-19 lockdown, and so we don't have a lot of data, and we need more participants really to build this idea out. Some takeaways for the group, over the year or 2 that we've been in this area. In-ear electrodes are promising, but have drawbacks. SSVEP, this is one of these things that seems to work. This notion of BCI literacy is something that needs a lot more investigation. And then I think we can be clever with how to tuck in SSVEP stimuli into other kinds of interfaces and interactions. Performance of dry electrodes is something we're very interested in, of course. Pupillometry is something that looks like it could be promising, and the integration with gaze trackers is something that's been mentioned a couple of times. Using pupil size as a measure of cognitive load could be very interesting, And I should note that HoloLens 2 has a pretty good built-in eye tracker that could be very interesting for these kinds of experiments. Another one that I think is very exciting, another idea is when you get into deep learning, I think what we really want is a big model with lots of data and lots of subjects, and then you fine tune that, right, for a specific individual, and that's how you could make some of these things more practical. Right, so you do a very quick calibration phase, but then you leverage the larger models in the same way that ImageNet is being used in computer vision tasks, right? This transfer learning is very important and popular these days. So I think that we need that kind of thing for BCI. And I think that is all. So these are some of our interns and the group. And I think that, yeah, that's all I've got for today. Any questions?
Well, thank you very much, Andy, especially given the timing. So I don't know if I should say it's very early in the morning or very late in the evening for you. Thank you for staying up that late with us. Are there any questions? In the meantime, I may have one myself. It's a bit tricky one, but you can. I will still proceed. As coming from the HCI community and Kai, what would you think if you could name one difficulty given the experience you had now with BCI? What would be the main challenge or difficulty that prevents BCI from being used as a general public as a general public interaction media? Like if you had a magic power that could leverage one challenge, what would it be?
Well, I think it's got to be the sensors, right? And how I don't think we have the right sensors, right? There's the smaller, more consumer-focused devices like the Emotive and the Muse. I think are primarily looking at EMG, right? Looking at muscle activation, and so there's moving beyond that, I think is the challenge. So if there was a series of dry electrodes you could use and it was comfortable, I think that would be a real breakthrough, right? Because then it would unlock a bunch of other things. I mean, that's just one thing that comes to mind. Maybe you ask the same question, in a couple of weeks, and I'll be thinking about something else. But definitely the ergonomics of what we got, I don't think makes sense yet for general populations of users. We're not there yet.
Well, thank you for your answer. I actually personally do agree with you. So do we have any other questions? So please feel free either to write on the chat on the YouTube feed or to just speak out if your mic's working. In the meantime, maybe I can just proceed and provide Thanos answers to Felix before, so regarding your question. So Thanos is saying that depending on the features we want to investigate in terms of model imagery, he would first assess ERDs, patterns between VR and non-VR. Then he says that now with the help of brain imaging, we can always find additional areas that are actually engaged during motor imagery and action observation that we could potentially use as EEG features. So that's regarding question of VR versus non-VR.
Right, great, thanks.
Okay, any other questions? If not, then thank you again, Andy. Now I'm pleased to introduce Lisa Wortmann, who is a PhD student at University of Bremen, working with Felix on attention and augmented reality, and who is actually one of the organizers with us of this workshop, but she had some issues with screen sharing. So now the stage is yours, Lisa.
Thank you. Can you hear me? Okay.
Yep, we do.
Okay, finally. I'm sorry for the delay and for the changes in the schedule. I actually had some technical difficulties that I hope are solved now. So my talk today is going to be on EEG-based brain-computer interfaces for attention-aware augmented reality interfaces. And I'm going to jump right in. Basically, the motivation for this research topic in general is to improve the usability of the head-mounted augmented reality displays. So that is because, on the one hand, the head-mounted displays do add very helpful and interesting information to our environment, while our surroundings are still visible. And it has the huge advantage that it's hands-free and you don't have to hold, for example, a phone in your hands. While on the other hand, the head-mounted displays might add more distractions because we cannot easily put the screen away since it's obviously mounted to our head. And also because the interaction can be more complicated because the gesture recognition or voice control might just not feel as intuitive as using a screen or a keyboard as we are used to. So the system we suggest is a user-based system for attention awareness. That means we start with a multimodal data recording while the system is being used, and then we have a real-time attentional state classifier that is then, and the information that comes out of this classifier is then used to either enhance task-relevant information that is shown on the AR device or to reduce the task-irrelevant information. And we hope that this would lead to distraction and more focus on the task. That includes 3 main steps. So in the first step, brain data needs to be recorded during the usage of the augmented reality system. We could think of different modalities to use. In this case, we have been working with EEG data. And then in a second step, we apply some sort of machine learning that analyzes the data, hopefully in as close to real time as possible, to classify the current attentional state of the user. The attentional state in this case is a very vague word because obviously it does entail quite a lot of different information because, for example, the attention can be directed at a certain object, or the attention can be directed internally, or maybe we want to differentiate, is the attention directed at something real or something virtual? And if my attention shifts, what was that shift about? Was it a self-motivated shift, or did just something catch my attention because it was very salient, and so on? So this attentional state is very diverse and can be looked at from a lot of different angles. And then in the third step basically is the adaptation of the AR interface that can be, for example, by displaying different objects or not displaying them, by changing saliencies, by changing placements, and so on. And that is very task dependent. That depends on whether you, want to catch the user's attention or specifically want to avoid distractions, for example. Okay. So the setup of our experiments usually like this. It includes some sort of device. In this photo, it's the HoloLens 1. And you need to find a setting that works the mobile EEG system and that doesn't interfere too much with the electrode placement. You need an analysis computer that works with the EEG data. And for some of our settings, we need eye trackers, depending on what we are measuring. So today, I specifically want to show a short overview over 3 of our studies. The first one is going to be about whether the attention is on real or virtual objects. So if we have a participant in a study and they are using a head-mounted display where virtual objects are displayed, but also sometimes maybe real objects are important, then maybe sometimes we want to know, is the attention currently on a real or a virtual object? In the second study, we wanted to differentiate whether the attention was directed internally or externally. Externally directed attention is whenever the subject needs information from the environment, like looking around a scene, counting objects, maybe just paying attention to a visual input. And internally directed attention is attention on thoughts, on memories, on and anything that really just doesn't require any sensory input. And the third study that I want to show you really is our first end-to-end system. It's an attention-aware smart home setting in AR. We did perform a short usability study that tested whether the smart home was rated as better usability if it was attention-aware compared to when it wasn't attention-aware. So the first study about real virtual objects was a memory game with either real or virtual cards in each trial. So as you can see here, we had a board game, and it had some virtual objects, as you can see the card stack on the top or the balls on the bottom. And then in this case, the cards that are displayed are real cards. And then in other trials, these cards were also virtual. They were also displayed by the AR headset. And we tried different field sizes to have different difficulty levels, and there was always some real and some virtual elements present. And then the task was for the participant to remember all the cards within 20 seconds. They had 20 seconds to look at all the cards, remember them, and then after 20 seconds, the cards were turned over and they had to recall the pairs as in a normal memory game. Okay, so we used 3-second windows of the EG data. These were non-overlapping, so from the 20 seconds, we discarded the first and the last second, and then we used 6 3-second windows from every remember phase, because in this remember phase, we were sure that the participants were actually paying attention to just this, these either real or virtual cards and not their surroundings. Then we did some very basic processing, pre-processing of the EG data, and afterwards classified the data with a shallow convolutional neural network that was built by another team. We just slightly adjusted it, and it's basically built analogously to a filter bank common spatial pattern analysis of EG data. And this classification was done offline. This wasn't an online study. We recorded the data and worked with it afterwards. And the training and testing were done in a person-dependent manner. So we took all the data and for every participant, trained the classifier and tested. What we did pay attention to for the results that you see here is that the train and test splits were so that no trials or no windows in the testing data were from the same trials as the windows in the training data, because we found that if we trained the model trial independently, we reached a classification accuracy of 93%, which was extraordinarily high. So we did trial sensitive analysis, and we reached an accuracy still on average above 70%. So based on 3-second windows from the EG data over all participants, we could tell that whether the attention was on real or virtual objects with an accuracy over 70%. In the second study, we did a spatial alignment task where, as you can see here, the participants saw a green tube on a wall, and the task was to keep the ball inside the tube. So the participants had to move. We especially wanted that movement because it's realistic for AR applications with head-mounted displays. The participants had to move so that the ball would always be aligned with the tube. As you can see right here, it's not aligned. It should be inside the tube. For the external conditions, again, that's whenever we depend on sensory input, in this case, visual sensory input, the ball is visible and we don't know anything about the movement, so we have to react to what we see and we constantly have to pay attention to the ball. And then for the internal trials, there was no ball visible, but the ball had to be imagined and the movement was described to the participants before. So for the data that we recorded, we did quite an extensive analysis. So we tested several window lengths, several classifiers, several modalities, and their combinations. For example, we checked whether 1, 2, 4, 7, or 14-second windows would work best. We tested an LDA, a random forest. We tested the same neural net as before. And what we found, if we aim at having a close to real-time classifier that in the best case even doesn't require training because it might work person independently, then the most promising combination would be a 4-second window with the shallow neural net that we talked about before. And EEG data did work better than eye tracking or the movement data that we recorded. But again, in this case, the classification was performed offline. We haven't done that in an online study with this setting. And we reached an accuracy for the 4-second windows of over 80% for a person-dependent classifier. The third was about the attention-aware smart home. The smart home itself was an SSVP-based smart home. It reacted to visual triggers around the room. So if a certain trigger entered the visual field of the participant, then tiles would show up, and these tiles flicker in different frequencies. And then the SSVP classifier would detect the required or the desired action. So in this example, a blind control was activated, and then the participant could either pay attention to the tile that said up, down, open, or close, and then that action will be performed. We added attention awareness by saying that constantly an attentional state classifier should classify whether the attention was directed internally or externally, and whenever it was directed internally, the system should not react to anything. So if it's internal attention and the visual triggers enters the visual field, nothing should happen. Only if the attention is directed externally. And then we did a usability study where we compared the attention aware version with the attention unaware version. Results are based on EEG and eye tracking classification. So this time it was real time, and we didn't include only EEG, but also eye tracking data. And we didn't use the neural net, but an LDA with features that were generated based on power spectral density. And the downside of this study is that we needed a person-dependent training phase before we could do the real usability. So the main part of the recordings were actually done just to record the training data, and then the usability study itself was not as long anymore. And for this training phase, we got an average five-fold cross-validation accuracy of 65% for these 1.5-second windows, which is not as high as in the other experiments that we did. And it led to an average error rate during the usability study of 50%, meaning in half of the cases where the attention was directed internally, the tiles did still show up. However, despite this high error rate, the system usability score and a distraction questionnaire still showed significantly better results for the attention aware system than for the attention unaware system. And these are the conclusions we have drawn from the study so far. So there are several aspects of attention that have to be taken into consideration. There's many things that you can still do. As I mentioned before, you can look at attention shifts and many other aspects. We did show that the adaptations do improve usability, and we can come up with a lot of scenarios where attention awareness would help the participants. we have a first end-to-end system that will be improved in the future. And the biggest problem or the biggest challenge that we're facing is person independence. Of course, with EEG data, that's basically always a challenge. But the training phase is something that really should be reduced to a minimum or even excluded completely. So maybe, yeah, person independence is one of the biggest goals at the moment. I did link the papers that were published from the papers before, and I want to thank, oh, sorry, I can't see you. Great. I do want to thank my supervisor, Felix, who's also in this session, and my professor, Dr. Tanja Schulz from the University of Bremen. Further questions, let me know, and thank you.
Thank you.
Thank you, Lisa, for your talk. I had some issues with the mic. Are there any questions in the room? I may leave you the floor, Felix. I think we have some questions on the YouTube feed. I'm not sure, so I'll go there and let you get here.
All right. Ask something.
Okay, so waiting for the question on YouTube. I may have a question myself to Lisa regarding the attention-aware smart home, because that's something we've also been working on. And I really like the idea of combining eye tracker with SSVP, but I just wanted to know, how did you actually do the combination of the data? Was it like one is the switch, the other is the command, or did you like mix the probabilities? So how did you mix between these two inputs?
In this case, for the attention-aware smart home, you need to differentiate for the SSVP detection and for the attention classifier. That was actually sort of different, because our focus in this study was on the attention classifier, and that was done by, well, we had a decision tree, basically, that is in the paper if you're interested. So if we had a certain certainty that the EEG result was good, we did use it, else we did the eye tracking, and in the end, if none were secure, we used the EEG.
Okay, so it was like to reinforce the EEG certainty. Okay, we have a question on YouTube from Piano Phantom, who's asking, what exactly do you mean by person independent when talking about the issues with EEG?
Yes, so the model must be trained first on data from that person. So for person-dependent models, we need training data. We train the model on the data of that participant, and then only that participant can use this model. That means so every classification is person dependent. Our goal would be to have a person independent classifier where no training data is necessary. That means I can use it, Felix can use it, anyone can use it without training. And the classifications work equally well for each participant, or work for each participant, let's say that.
Thank you for your answer. Are there any further questions on any modality? Okay, then thank you again, Lisa, for your talk. I think we may proceed with our last speaker of the day. Mark, are you here?
Yeah, Mark, are you ready? Or
because there is a break as well.
Small break. So Mark was having some issues with connecting to the screen share, as some of us had as well, and he is working hard on fixing it, but I think he's in the last stages.
Yeah, I think we could maybe take the break right now and then come back in 10 minutes. It's been some talks now in a row, so we can have a small break and then come back in 10 minutes.
Yeah, let's do that. We meet here again in 10 minutes. Don't miss the last presentation and our final discussion. These will surely be highlights. So
see you.
Talk to you soon.
Hello, 1, 2, 3. Hello.
Awesome. Hi, Mark.
Can you hear me?
Yes, I do.
Yep.
Oh, great. Okay, good. That's
Perfect.
great.
So is your screen sharing working as well?
Well, I put my thing on the main screen. Can you see it there?
No. Google.
I can see it fine on my view.
From my side, I only see Google. Maybe you can try another screen, like the one that Lisa was using.
Sure. Okay, let's go over there.
Are you giving a live presentation?
Okay, so
Yep, now it's working.
Now it's working.
Perfect. So I can introduce. Normally, everybody's back again here. We can start. So again, and thanks for remaining with us. I don't know what your time zones are. I'm very happy to announce our last speaker of the day. Mark Billingers is Professor of Human-Computer Interaction at the University of South Australia in Adelaide. He has significantly contributed to the field of XR in the world, and he is the recipient of the 2013 IEEE VR Technical Achievement Award. Without further ado, Mark, the stage is yours.
Great. I hope you can hear me okay. I'm sorry for the delay. I had to make some changes. Oh, this isn't audio. Okay, I can fix my audio. Give me a second.
No, it should be fine now when I cut mine.
Fine now? Okay, great. So I'm going. Is it okay?
Yes.
Great. Okay, great. So I'm going to talk today about brain synchronization and brain-computer interfaces. So the basic idea is, can my thoughts influence yours? And it turns out that for the last 10 years or so, people have been studying or using hyperscan to study brain synchronization. So hyperscanning is where you have two people who are doing the same task, and at the same time you're measuring their brain activity using EEG. So for example, you may in an fMRI machine, or two people sitting side by side with EEG, or even two people with FNIRS. So here's a video that gives an example of hyperscanning being used for two people playing the violin. And first of all, you'll see two people playing in synchrony, and then you'll see two people playing out of synchrony, and you'll be able to see the two brain activities.
I think we don't see the video, do we?
Oh, is there no video?
Yeah, it seems it's still on the slide where there are the two brains facing each other.
Okay. I'm not quite sure what to do about that. Well, I guess I can just keep on talking without the video. I'm sorry about that. So let me just go to the next slide.
Now we see the slides.
Okay, great. So with brain synchronization, the idea is that you can take the brain signals from two electrodes, and you can look at the phase of the two electrode signals, and sometimes the phase will be in synchronization, sometimes not, so as you can see from the graph here. And you can use a phase locking value analysis, which basically measures the phase of two electrodes and sees whether the waves are going up or down. So this has been the area that's relatively recent area of research, only being studied really actively since 2002. And there's an excellent review paper here that talks about that. And until now, there's been really no hyperscanning research done in AR or VR. So there have been some previous tasks done that would be ideal for AR and VR. So this slide here shows a list of some of the tasks. So for example, there's imitation tasks where you have to match somebody else's hand motions, coordination tasks where you try and tap footsteps together or fingers together, coordination tasks like the visual search task or cooperation between strangers versus partners. And there are some tasks which aren't so suitable for brain synchronization in AR or VR, such as eye contact or economic games or interaction in natural scenarios. So some of the benefits of brain synchronization, when people have been engaging in a task and they start having brain synchronization, then they report feelings of flow, or they get into a flow state. They report better collaboration, increased trust, greater social presence, better group social dynamics, and other benefits as well. So one of the classic studies for brain synchronization is finger tracking, and you can see here's an example of that study being done. So, and this is a study we did ourselves. So you can put opposite somebody and point your finger at them, and then as they move the hand around, then your fingers move to follow the hand. So you have 3 stages in the task. First of all, you sit opposite them, just pointing the finger, not moving. Then you, one person's the follower, and you move around. And then at the end of the task, you sit still again. So this is a classic. Hakeem was saying the slides aren't changing. Is that right?
Yeah, we were with the brain synchronization. Now it's pre-training. I don't think it seems like we can change them manually.
Okay.
Sorry.
Okay. Well, it's not very good, is it? Let me see what can be done about that. Okay.
Okay, yeah, now we changed to post-training.
Now it's working properly?
Yeah, now it's
okay.
On the post-training.
It should be on finger tracking now. Now it should be on pre-training. Is it pre-training?
No, brain synchronization it says now.
It should be on pre-training right now, is that right?
It's on brain synchronization in VR.
Oh, okay. This is a disaster.
That's magic.
I'm really sorry. This is just not working. Well, I will.
Maybe
sure
you can share the slides on the Trobadis and can share the screen.
What do you want me to do?
I don't know if you can implement that, but if the slides are uploaded somewhere, maybe someone else can share the screen.
Yeah. I'm not uploaded anywhere else, so but I can try showing my screen, but this is probably not going to work because previously it didn't work. So
we see your screen right now.
Yes, the problem is you're only going to see others, unfortunately. So let me see the present mode now. So you're only seeing
See part of your slides.
What did you say, sir?
We now see part of your slides. Bottom
exactly.
corner.
Yeah, exactly. That's the problem. I'm not sure what to do about it. So it seems what I need to do is upload the URL to the presentation tool.
Or maybe you can keep it not full screen, maybe you can just, we can see your screen, so you can just slide through the list of the slides from the software you're using.
Okay,
full screen.
Let me try that then. Thanks. I'm really sorry about this. I anticipate this episode talks. I'm not sure if other people have an issue, so let me see if I.
Like this.
Part of the slides.
Fine.
Sorry, this is not very good at all. Okay. I go back to here. Actually, I can. Well, yeah. Let me go back to here. You can see the finger tracking experiment up, and
Yes.
right here is showing measuring the brain activity. So before finger tracking starts, you can see the two people's heads. The black dots here are the electrode positions. And then while people are tracking their fingers, you can see some arcs locating those two left person's head, and that shows that those electrodes are in synchronization. But the interesting thing happens when people stop tracking their fingers, and you see, actually, if I zoom in a little more, maybe. Just a little bit more here. Okay. So the interesting thing is when people stop tracking again, now what you see at the end of the session, there's a lot of arcs between each of the heads, and that means that each of these electrodes are now a single person. So the really remarkable thing is that even people are no longer moving their fingers again now, because they've done this finger tracking exercise. Now the electrodes on the head get in synchronization with each other. So after our first experiment, we then ran an experiment inside VR. So now you can see the two people sitting together, and of course you don't need to look at each other because they can be facing, because they're inside VR. And the main hypothesis was that we thought that VR could be used to reproduce brain synchronization and face-to-face, and we could use VR to enhance synchronization. So this video, I'm not sure how it will work. Loading in a second. In that video, you can see the two avatars sitting in VR, and one person's moving the hand, and the other person's hand is following it alongside. So we're doing the same brain stimulation task we did before, but now we're doing it inside VR. But of course, the interesting thing with VR is that you can change your body. In particular, you can put your body inside somebody else's body. We also did a follow-up test, and this shows it here. And so now the person's body is the other person's body. And you can see when they look down, I can see a hand, and two pieces of hands come out of my body, and so I can follow the hands. The theory was that because now both people have exactly the same perceptual cues, brain synchronization may occur more often. We did the study, and we measured the number of electrodes that were synchronized with each other, and we can see that very well. But we found that in the task, the other ones, we had synchronization happening in the beta and theta frequencies, and you can see that pre-training we had 160 brain connections or electrode connections. Then after training, 210 or 209, so there's a significant difference. In the face-to-face case, we found electrode synchronizing alpha band, going from 154 to 97. And then in the first-person perspective, we found synchronization happening in the beta band, going from 141 to 196. So that's interesting and encouraging. But this is just very beginning stages. I think what we found is that we can use VR to reproduce face-to-face studies at brain synchronization, but we need to study it a lot more. And in this here, it shows, hard to see, but this is the two brains with the red dot showing where electrodes are. The bands represent the number of connections between the electrodes. Before the training starts, you'd expect to be a low number of connections, mostly happening just chunks. And now in the second slide here, you see post-training, you have these strong red bands, and this shows a number of connections happening between both of the electrodes. So we just published a paper about this, so if you please send me an email or send me a message, I can send you a copy of the paper. The first example of brain synchronization done inside VR comparing to the real environment. What's particularly interesting about this, though, is new ones that can be used to bring this back into more consumer VR. Particularly, NextMind, for example, are selling for $400 a set of BCI electrodes you can mount on the back of the head mount display. And there's a company that makes elusive link that sits in the foam pad of the HTC Vive and electrodes that come out forward. So we're very interested in how we can create experiences that create this information. And earlier or late last year, we created an application called Neurodrum, which is a drumming application which you put them together, and they could measure the brain activity while they're drumming. And if the brain starts synchronizing, then we provided more visual feedback. Play the video of this, you can hear the auditory going as well.
Neurodrum is a VR drum experience that allows players to drum together while their brain signals are simultaneous. At first, you can set some daily objects on a table to use drums. The player will use 2 drumming sticks to play the game. Both the players will wear an EEG capturing hardware to get the signals measured from the frontal lobe. The data acquired will be streamed to the data processing system to enhance VR experience, depending on the player's collaborative performance. We designed a software to calculate the phase locking value, which is an index of neurophonicity, for the FP1 and FP2 channels of the theta band from both the participants. When synchronization between 2 players is low, the camera will be more clear, whereas when synchronization is high, the vision becomes more obscured, with each cloud eliciting higher. We logged and analyzed the user's brain signals, as well as the matter of subjective question.
Okay, I'll stop the video there. As it showed in the video, what happens is we start playing this experience. 2 people drumming, and we chose drumming because it's a task that naturally introduces synchronization. And then when we measure the electrodes on the forehead, the brain activity electrodes on the forehead, and at the beginning, when they're not very synchronized, they can see a partner across the table in a almost augmented reality view. But as they start more and more synchronized, we start producing more particle effects, and we change the transparency of the video effect, and so they can't see their partner anymore, and so they get a lot more graphic feedback as well. We did this at SIGGRAPH Asia last year. We measured people's response. People who reported, who exhibited a high level of synchronization, also reported enjoyment playing with their partners. So what we're going to do next is run another experiment now. I'm looking at the effect of eye gaze, and I'm particularly looking at what happens when you do a synchronization task with and without realistic gaze, or putting a good gaze where the character deliberately looks away from you. You can use the HTC Vive with the eye tracking built in. OpenBCI Brain and Lucid Link also measure brain activity, and we can standard LVs to method to measure brain synchronization. To look at social preferences, communication users. And this little video here shows an example of a character you can have that will realistic eye behaviors. As a character where the eye patterns and the blinking and the action is all being driven by the inside the HTC Vive. So we can use this character in a shared finger tracking task before, but now because we've got eye gaze, we have much more avatars. So just to wrap up, what we talked about today is how we can use VR to create brain synchronization, and we can reproduce real-world behavior. And we can also look at novel VR properties to enhance information, such as putting versus body. And there's many directions for future research. And some work with VR and brain synchronization. We can also look at AR as well. And we're about a second study looking at gaze and how gaze might affect brain synchronization tasks. And here's my contact details. I'm really sorry about the trouble with the presentation. If you'd like a copy of the presentation, please send me an email and I'll send you a copy. And also the videos as well. So thank you very much for your time.
Thank you very much, Mark, for your presentation. I think there is an echo from me. Maybe Felix, you can take on.
Yeah, any questions here?
Same apparently. I will go on the YouTube feed. So please, I will maybe drop the YouTube link if some people are too shy to talk in public. Maybe you can drop a question on YouTube.
I have a question regarding the synchronization. Do you think that would also work with tasks where the two persons do not do exactly the same thing? So maybe there's one person talking and the other person is listening, or one person is performing something and the other person is watching. Do you think that's also something where you could observe synchronity or asynchronity?
Oh, that's a question. The papers that I've read all try to get users to do similar tasks, but they do have representation happening in other cases. So, for example, there's Susan Dyker from New York, a very nice study looking at people learning in class. She had people, 12 people wearing EEG for a whole semester, so 12 or 13 classes. She measured their activity through the whole class. Then she looked at, in the class they're doing many activities. You know, they were as a lecturer, but they were also writing notes and doing their own thing. And then she found there was some brain synchronization that happened there, even though they're doing many different activities. And the students that synchronized with the students that had the highest grade also had a great improvement as well compared to the students that did not have. I think there are some examples where you could have people doing tasks of several activities, and they may not necessarily be doing the same activities at the same time, but still have periodic synchronization as well.
Wow, very cool. Thanks.
Well, we have a small question from the YouTube chat, and something is asking, I wanted to know why both Lucid Link and OpenBCI are being used.
That's a question. We want to use them both together because so the OpenBCI covers the whole head and to wear a whole brain. And what we're trying to test is if the link is only covering the head, so it's much more convenient to wear with the VR headset, but 6 electrodes in the forehead. So what we're hoping is that even though we don't have the whole head covered, we can still get some synchronization signals just coming from the forehead. But what the reason we're using both together is we want to use the OpenBCI as a great to be able to measure all of the head brain activity, and then to see if the brain synchronization across the whole head, if some of that will also go to synchronization just in the first few electrodes. That's my motivation for doing that.
Any further questions? Okay, then I think Anatol suggested that we could take a group picture with no virtual social distancing. But I think we may do it right after the panel. What do you think, Felix? Should we start with the panel?
Sorry, say again. I had audio issues just now.
It's fine. I was mentioning that Anatol suggested that all the participants to the workshop could have a group picture with no social distancing. It's gonna do good for all of us not to have to worry about social distance. So should we do it now or maybe after the panel, a short panel?
Why not do it now? Now we still have a lot of people here.
Yeah, I think so as well. So I don't know, maybe someone from the country, people can like group together somewhere, and then somebody can take a screenshot. Joao, can you take care of that? And Mark, maybe you can stop sharing your screen. I don't know if you want to.
We are all synchronizing, right? Everybody's looking in the same direction towards the middle of the room.
Yep, everybody look at Joao.
All right, everybody explored the remote menu. Do we have a picture?
Yeah, I see Joao trying to do it on the YouTube feed, so we're nearly there. Is it done, Joao? Okay, perfect. Thank you. Well, then maybe we can proceed with our last, and that maybe helped us all get a bit more awake than we were for people who were maybe too late in the time zone. So the idea was maybe have some sort of open and maybe lighter discussions with all of our speakers. So I would maybe ask the speakers to join, or they could be identified with us, Felix and I, and Lisa, if you could maybe join us. Yeah, so that you can all be identified. Awesome. So feel free to ask questions through just taking the mic or through the chat. I would probably start myself by asking the speakers some questions, and then you can answer by turn. But I was really wondering, what was actually your first experience with BCI or VR? If you are more from VR field, what was your expectations, and what made you think about, oh, I should try out BCI? What were your expectations, and what were your results? Maybe you can start, Mark.
Okay, can you hear me okay?
Yes. Yes.
So I've been doing VR for a long time. So actually I've been doing VR since 1989. So it's a really long time. And my first experience with VR was just being amazed to be able to be in this incredible computer graphics environment, even though at that time we only had displays that were 320 by 240 pixel resolutions. So it was kind of crazy. My experience with BCI is much more recent. I think I first started using BCI systems maybe 4 or 5 years ago. I first saw some demonstrations of people using very simple NeuroSky and single electrode systems to connect up with little AR and VR demos. And in my lab, we started using EEG about 2 years ago. So we're only starting recently in the field.
Okay, and what were your expectations with that? So were you expecting something? Did you get disappointed, or it's just to give an idea maybe to people who would like to start also working on BCI?
It was surprising to me how difficult it was for some of the BCI, and so I'm really grateful for Anatole and for the others who've made BCI easy to use, OpenVibe and other software tools and the BCI with hardware tools. But even with some of those tools, with some of the experiments we've taken, it takes a long time to collect data, and it takes a long time to process the data. So that's one of the surprising things to me when I came from outside BCI, from doing AR and VR experiments. We could do experiments in a month or so, and collect some data and have some results. It seems like with EEG-related experiments, it takes at least 2 to 3 months to collect the data, and it can take another couple of months to analyze it. So you've been pretty well if you can do one experiment in 4 to 5 months compared to VR. So it's a lot more complicated, but it's getting much easier. So thanks to the work of Anatole and others who've made these really great tools, it's very much easier, and it's going to continue easier. So it's a very exciting field to work in, I think.
Thank you very much. Any of the other speakers want to tell us a funny story or something about their expectation and how it happened first time they used the BCI? Andy, maybe? I think it's much more recent using BCI. I knew something about it. Can you tell us what were the expectation maybe of MSR and in the end how it happened?
Well, I'm a little bit surprised. The first time I tried a BCI interface was the Brain Ball demo that made the rounds. Like, I'm gonna say early 2000s, and that I forget which group did that. This was a really funny experience where you had an electromagnetically controlled ball on the middle of a table, and the person who had kind of the longest stretch of alpha, the ball would roll towards them, right? So it was one of these funny demos where, like, when you realize you're winning, you get excited and then you start losing because you're excited. Like the goal is to relax, right? And I thought that was just a very clever thing. I think it was called Brain Ball. And the neat thing about that, of course, was that they didn't have to do any really sophisticated processing there. It was just looking at, comparing the relative, or comparing the difference of the two responses. And I thought that was really ingenious, and that's kind of stuck with me a little bit. So looking for these little tricks in the processing in BCI is, I think, even though maybe it was a kind of a goofy demo, I thought it had a little kernel of something really interesting there.
Yeah, I think it's called the MindFlex, if I recall, and that's funny because that's actually as well one of the first demos of BCI that I've seen. I've never had the occasion to try it, but when I've seen it, I remember I was an undergrad student. I was completely amazed with that, and yeah, one of the reasons I decided to start working on this. Thanos, is your mic working? Maybe, or Bridget, if there's an issue with the mic, maybe about the opposite. I don't know if maybe you want to tell us something about how you started working on either BCI or VR, or did you start from the beginning working on both of them?
Well, I got in touch with the field through internship at Niels Bierbarmer's lab. And there I was involved in a rehabilitation study where prosthesis was controlled by stroke patients through a brain-computer interface. And this really caught me, this idea that you could do rehabilitation with these patients through brain-computer interfaces. And later on, I did some studies on body ownership. And through that, I got I heard about the lab of Mel Slater and Maria Sanchez-Vives, and then did my PhD there. So this is kind of how it came together that I then used BCI in VR.
I see.
Yeah.
Thanks. Maybe Felix, would you have a comment on that? I don't recall either if you started by BCI or VR, and maybe Thanos.
Can you hear me now?
Yes, we do hear you.
I think it's working. Okay, finally. I had to remove the Oculus because it was blocking everything. Okay. So, well, answering also your question, I initially actually came from the VR world. So through VR, I went into rehabilitation, so virtual rehabilitation, and then through rehabilitation through VR into the BCI with VR for rehabilitation. So it was like a stepwise way.
I see. And what were your expectations with BCI when you started working on them? And then how are those expectations met, or are you still waiting?
Right. So they were really great in the beginning. Then it was like, a downslope where you actually see and the actual complexity of BCI system, because in general the BCI world is a multidisciplinary field, so you need to acquire knowledge from many different fields, and it was a little bit hard in the beginning, but in the end I think it really pays off, especially when you start getting some really interesting clinical data and you see the actual impact that it might have in people's lives. So I think it was actually the really nice turn in my studies that I followed the BCI route.
I see. Thanks. I don't know if Anatol's mic is working, but I think he's also coming from the. Well, I know that he's coming from the VR world, and he was one of the first to introduce BCI in France and with the Open Vibe project. Maybe you can also answer to that, Anatol, and have some nice anecdote on the chat. In the meantime, maybe Felix, one last question. Could you maybe what would be your advice to anybody who would like to start working on BCI? Would like to jump on hands-on, or what would be the small tip to somebody who would be interested in doing some BCI in the future from the iSmart community?
Yeah, I think the best thing is just not to be afraid. I mean, I think it's worthwhile to look into the simpler more cheap devices if budget is a concern. But I would also advise not to still try to look at what you actually capture there. I mean, it's really a whole world to explore there. If you look at the signals you record and what's happening there. So try not to use the BCI as a black box, but also look into these. But I mean, right now there are a lot of really nice tools which support you to get started, right? I mean, there's the OpenVibe. There are a lot of good Python tools if that's your jam. If there's really a lot of tool support which allows you to get started with the difficult things and get learning there. They also all provide nice visualization, for example. Real-time support. So if you pick up one of these tools, I think building a simple BCI, for example, I mean we saw a lot of examples using the SSVP BCIs. I think if you just want to get started, I think that's a good starting point, because that's one of the BCI paradigms that is known to work quite robustly, and that I think that gives you some kind of feeling of success if you build your first BCI with that. So that's I think a nice starting point there, and from there develop towards whatever you are looking for. But there you get some initial validation, I think, and that's a good thing to have.
Well, thanks, Felix, and I can only really much agree and emphasize over this idea of not maybe using BCI as black box, but trying more to rely on well documented paradigms. I have also a comment from Anatol that I would speak out loud, who said he would recommend to be in contact / collaboration with neuroscience folks is possible, and be ready for a couple of experiments which are not conclusive. Yeah, that's absolutely the case. It's always better to have people from neuroscience field, and again, which means what you were saying, Felix, not to use BCI as a black box, and also Anatol, this idea of that it's going to be a lot of experiment, non-conclusive, but you should not give up and continue. Maybe Lisa, you can, as a closing word, maybe you can give us maybe a story or your insight about when you started your PhD on BCI and VR. I know, for having done quite so myself, that it's maybe challenging to use these two technologies together.
Yes, I studied cognitive science, so I do come from both sides. Basically, I did get quite of the foundations in neuroscience and psychology in that side, and also got my hands on the coding and the practical stuff. So I thought of BCIs always. I thought of a very interesting topic, and I was very happy when I got the opportunity to work on this topic with Felix in my PhD, and I'm still very appreciative of it. I don't know. I feel like there's a lot to explore, and I love how Felix pushes me to look inside the data and really understand what I'm doing. I think there's a lot of potential there, but I understand how it can be frustrating for people that are used to doing experiments and getting results and understanding them right away.
Yeah, absolutely. I completely know that feel. Well, I think we're miraculously right on schedule, maybe a couple of minutes late, and it's the occasion for me to first of all thank all the speakers for agreeing to join us during this workshop. Some very, very late. It's really appreciated, and thank you again for the talks. We would like to also to apologize for all the technical issues that happened, but I think overall it went pretty fine. I would also like to thank Felix, Anatol, Lisa for organizing this workshop with me. I hope you had an enjoyable time as enjoyable time as I had, and I hope maybe this helped you have a more insight about what it's been conducted in BCI and VR together, and maybe that would also trigger some collaborations in both the fields. So, well, thank you very much again, and I hope to see you in person soon, very soon, all in person. Thanks.
And thank you, Kim, as well.
Thank you.
Well, thank you very much.
Right, then have a great conference.